Hello, in this video we'll introduce the BigO notation and the complexity theory subject. And in order to facilitate this introduction, I thought I would make use of a simple analogy. You're probably familiar with something like this. These are padlocks that you use to lock your stuff in a gym, for example in the gym locker, and they have these 3 dials, or they can have more, in order to provide a combination for you to lock your stuff. Let me show it to you on the close-up camera. As you can see, this padlock has 3 dials. I can turn each dial independently to give me a different code. And one particular code in this padlock would open this lock. Now let's say you forgot the combination for your locks and you need to get to your stuff, and we need to find a procedure on how to open this lock, or how to open any lock for that matter, without knowing the combination. One way to do this is to go through every single combination. So for example, in this particular lock, which has 3 dials, we would set the combination to be 0 on the first dial, 0 on the second one, and also 0 to the last one. And then we would try each combination. We start with 1, try to open it, 2, try to open it, 3, try to open it, and so on. 4, 5, 6, 7, 8, 9, 10, and so on, until we go through every single possible combination in the lock. Now obviously this is not a very practical way of discovering the code, but it will work. If we go through every single digit that we have in our 3 dials, we will eventually find our code to open the lock. Let's try to find out how many steps we need to perform in order to ensure that we open this lock. To calculate the total number of combinations of this padlock with 3 dials, we can start from 0, 0, 0, our first combination, and then go up to 9, 9, 9, the last combination. This means that we have gone through 1000 different combinations, which is the 0, 0, 0 plus the 9, 9, 9, so 999 plus 1. If we do 1 combination per second, this means that we are going to take more or less around 1000 seconds to complete all the combinations to guarantee that we can open this padlock. There's another way we can calculate this. If you see over here, you can, let me just focus on the padlock. This, as you can see over here, this dial has from 0 to 9 combinations, right? All the numbers from 0 to 9. So in order to calculate all the combinations, we just need to do 10, which is the 0 to 9 combinations, times another 10, times another 10. These 10s are simply the 0 to 9 combinations. There are 10 combinations we can try on each dial. If we do 10 times 10 times 10, this of course gives us 1000. Another way to write this is to do 10 to the power of 3. This is just a different way of writing 10 times 10 times 10. Now let's make our life a little bit harder by increasing the complexity of the problem. Instead of using a padlock with 3 dials, let's use a bigger one. This one has 4 dials, and let me show it to you on the close-up camera. And we can adopt the same strategy that we had before. We can set all of these dials to 0, right? So we have 4 zeros. And then we try each combination one at a time. We start with 1, and then we try 2. Of course, we have to remember each time to try to open it. Then 3, 4, 5, 6, 7, 8, 9, then 10, and so on. We keep on trying to open it each time with a different combination until we get to the last number, which is 9, 9, and here the final 9. Now let's try to repeat the same exercise that we did before with this bigger padlock, the one that has 4 dials. We can use the same technique that we used before for the 3 dial padlock. We do 10 times 10 times 10 times 10, because we have 10 combinations on each dial. This gives us 10,000 as a result. And if we took 1 second per combination, we would spend a total of 10,000 seconds to open this padlock. And again, we can rewrite this in a different notation. We can simply say 10 to the power of 4, which means 10 times 10 times 10 times 10. Between the padlock with 3 dials and the one with 4, there's a factor of 10 increase of work. More or less, for 3 dials it would take us between 15 to 20 minutes to go through all the combinations, and with the 4 dials padlock, the bigger one, it would take us 10 times as much, almost 3 hours. You can kind of see where this is going. If we had a padlock with 5 dials instead of 4, this would take us 10 to the power of 5 combinations, which is around 100,000 seconds if we take 1 second per operation. So you can see where this is going. If we had a bigger padlock, let's say with 6 dials, we would have 10 to the power of 6. If we had one with 7, it would be 10 to the power of 7, and so on. If we try to generalize it, if we use a variable instead of a concrete number, we would have an expression that would give us the number of steps that we need to perform depending on the size of the padlock. So for example, if we use the letter n, the variable n, to tell us how many dials our lock has, the expression would be 10 to the power of n. This will tell us exactly how many steps we need to perform to open our padlock. If we replace n with the number of dials that our padlock has, this expression will give us the number of steps that we need to perform in order to unlock our padlock. In this analogy, these padlocks are the inputs to our algorithm. Specifically, the number of dials that they have is the input size to our algorithm. And the algorithm is our mechanism of trying every single combination that is present in the padlock. How many steps the algorithm performs is given by the expression that we have just written, the 10 to the power of n. This is what BigONotation gives us, a notation that tells us how many steps the algorithm will perform with regards to its input. If we had to write this in BigONotation, we would write BigO, and then in brackets we would write the expression that we have just written, the 10 to the power of n. This is the number of steps that we need to perform to guarantee that we open this padlock. We can also write it as big O of c of n, c being the constant of 10. What this notation is telling us is the number of steps our algorithm will perform with regards to its input size. In this case, the input size is the padlock itself, the number of dials that it has on the padlock. In this particular example, the scalability is very bad because every time we add 1 dial, we are increasing the number of steps by a factor of 10. As a small exercise before you proceed to the next video, you could try to come up with the BigO notation of trying to crack open this particular padlock. This padlock over here has all the letters in the English alphabet from A to Z, only in uppercase, and try to come up with the expression, the BigO expression, of going through every single combination of this padlock. Also try to solve it for the general case. This particular picture over here only has 5 dials, but imagine we had n dials instead of 5. But again using the English alphabet from A to Z instead of the numbers from 0 to 9. Hello, in this video we will try to crack open this padlock in a different manner that doesn't involve going through every single combination just like we did in the previous video. This is similar to when you are writing your algorithm to the same problem. You might have a different way of solving it, and you need to choose between 2 different implementations or 2 different algorithms. The BigONotation gives us a tool to decide which algorithm scales better with the input size. But first, let me show you how we can open this padlock. What we need to crack open this padlock in a faster way is some plastic explosive and a very simple circuit. And with the plastic explosive, we just need to stick it on the arm over here. We just have to be a bit careful with this stuff, stick it all around, and then we just grab this metal electric rod, we stick it in slowly into the explosive, we stand a little bit back, and then we just press this button. And nothing happens. Nothing happens because this is not really plastic explosive, it's just that stuff you use to stick things on the wall. But you get the idea. Now we have a way to open these padlocks which is independent on the number of dials that we have. It doesn't matter how big the padlock is, how many dials we have, we will still take more or less the same amount of time. Remember that in this analogy, the number of padlocks that we have represent the input size to our algorithm. So when we are using this way to open the padlock, we are independent of the input size to our algorithm. So this manner of opening the padlock is a lot more scalable than the previous manner, the one where we were trying all the combinations one after the other. So really the number of steps that we need to do to open a padlock with 4 dials is just one step, that of pressing the button. And this is true whether we have 4 dials or whether we have the previous padlock with 3 dials, or for that matter any dial, who still will take one step. In BigO notation we write BigO of 1. Or we can also say that our algorithm has a constant runtime performance. We say that the algorithm is constant because it will always give you the same constant time to execute, irrelevant of the input size that you give it. Let's say our manner of exploding the padlock, which requires setting up the circuit and putting the plastic explosive and so on, let's say that takes about an hour to set up. You'll probably be better off if the padlock is small. If it has, for example, 3 dials, you'll be better off with the first method, the one of trying out all the combinations, because that will probably be quicker. It will take you maybe 15 minutes to open it. However, if you have a bigger padlock, let's say with 6 or 7 different dials, it will be much faster, right? Because you will not be able to open that padlock by trying out all the combinations in less than an hour. And this is why the BigO notation does not tell you how fast or slow an algorithm is. It's simply telling you how well it scales. The 2 expressions that we have talked about, the exponential one, the 10 to the power of n, and the one, the BigO of 1, are expressions at the opposite end of the scalability scale. These are called functional complexity classes. The exponential one, the 10 to the power of n, is the least scalable one, and the constant one, the BigO of 1, is the most scalable one. What we will do in the next video is to go into more detail on this notation and also have a quick glimpse at different complexity classes. Hello and welcome. In this video we will be talking about the different complexity functional classes. But before we go into a little bit more detail about this topic, I thought I would try to explain the concept of scalability. And to help me with this, I thought I would quote a fairly famous software engineer called Grady Botch. And in his own words, he says that one does not reach the moon by building a taller ladder. I wanted to use his quote. Actually, this was a tweet that he did, because I think this really explains scalability very well. Think, for example, about using a ladder to climb to a fairly sized tree, or, for example, to get to the second level of a building. And in that sense, a ladder is a solution to a problem, right? You want to get to a certain level, to a certain height, and you use the ladder to get to it. However, the higher you go, the more problems you start running into. Once you reach a certain level, you will not be able to use the ladder anymore because the ladder becomes heavy, it might get wobbly, it starts being problematic. We say that you are reaching its scalability limit, or the problem that you're trying to solve with that particular solution becomes intractable. As you need more height, as you, for example, need to reach the 10th or the 20th floor, you start using different tools, different solutions, maybe a rope, or if you need to climb even higher, maybe a helicopter. If you eventually need to reach the moon, you will need something like a spaceship, but basically you will have to use different solutions. So this is what we mean by scalability. The solution that you have, your algorithm, right, your code, will only scale up to a certain input size. After that, it will become so slow that it will not be very usable. Think about our previous videos where we were trying to unlock the padlock by going through every single combination. If we had a big enough padlock of, let's say, 10 dials, it would take us hundreds and hundreds of years to be able to go through all the combinations. It's not really a solution for that type of padlock. Again, the problem becomes intractable with that solution. This is what we're trying to measure with complexity functional classes. In our previous videos, we have discussed already two of these classes, the exponential and the constant one. These are on opposite sides of the scalability scales. We can think about the exponential as being the ladder. It will allow us to solve a small problem. If we want to get to the second level, we're fine to use a ladder. Similarly, if we want to solve a problem that only has a small input size, we're probably fine by using an exponential complexity algorithm. However, as we increase the size of our input, the solution will not scale. The problem will become intractable. So we would need to design more scalable algorithms. And to measure these more scalable algorithms, we have all these different complexity classes. We have the quadratic, the log linear, the logarithmic, and the constant. The constant we have already seen in the padlock videos, the ones where we were breaking that padlock. These aren't all the complexity functional classes. There's a lot more. However, these are the main ones. And also, if you know about these, you'll be fine with all the others as well, as long as you understand the concept. But in summary, when we write an algorithm, it will belong to one of these complexity functional class, and it will tell us how scalable that solution is with regards to the input size of our algorithm. Another thing that's important to mention about these complexity functional classes is that they're not just about speed. They're not just about time of execution. We typically call this runtime complexity. When you write an algorithm, you want to know its runtime complexity, whether it's an exponential, whether it's a linear, logarithmic, and so on. But sometimes we use these complexity functional classes to also measure things like memory, network usage, disk usage, and so on. For example, we can say that an algorithm has a constant runtime complexity, however, it's using a linear amount of memory. In this course, we will mainly focus around runtime complexities, and we will discuss and show examples of the main functional classes. The other thing is that when we come to measure an algorithm to determine what is its complexity functional class, it's not just about measuring one metric. There are three cases. There's the worst, there's the average, and there's the best case. If we had to continue with the analogy of the padlock, the solution to go through every single combination of the padlock has a worst runtime complexity of the exponential class, the c to the power of n. The worst case happens when the code is set to the last number of our combination. For example, if we had 4 dials, the worst case is when we get to the very end, the 999, because we need to go through every single combination before we crack open this padlock. The best case is on the opposite end. The best case is when the padlock is set to 000, which is our starting position, and in our starting position, the padlock will open immediately. So in that case, we have a runtime complexity of order 1. The average case is when you go through all possible combinations and you find the average. For the padlock, it is the exponential runtime complexity division by 2. This is when the combination is set more or less somewhere in the middle. However, a rule of BigO notation is to always remove constants from our expressions. So in that case, we drop the 2 and we leave it as an exponential. So basically we're saying that the average and the worst case are more or less the same. It's just saying that they scale more or less at the same rate. We will talk more about these rules in the next slides. But basically whenever we mention the BigO notation of an algorithm, it can always be referring to the worst case, the average, or the best case. It is usually specified. If it's not specified, we usually assume that it is the worst case. The reason the worst case is used more often is because it's easier to compare different algorithms together. If you say that in the worst case, one algorithm performs better than another one, then in every case it will perform better. So usually the worst case is the most meaningful metric to use. In this course, when we are developing our different algorithms, our different pieces of code, we will talk about both the best case and the worst case. But keep in mind that whenever you are comparing algorithms, you are usually using the worst case. If we take the other solution, the one of cracking the arm of the lock open, the worst case, the average, and the best case is always constant. There is no best and worst case. There's no relation to the input size of our padlock that will make the worst and the best case different. It will always be constant. Now let's talk a little bit about the rules of the big O notation. Whenever we write those expressions, what rules should we follow? There's two rules. The first rule is to always drop a constant. We saw this on the previous slide. So if we have an expression, something like this, 2n to the power of 2 plus 4, we drop the constant 2, we drop the constant 4, and that becomes big O of n squared, or n to the power of 2. We just drop any constant in there. The reason we drop constant in big O notation is because, remember, we are measuring scalability. And when we measure scalability, we want to measure it as it approaches infinity. So think about n as it is approaching infinity. How will it grow? It doesn't really matter if it has plus 4. At the end, it is still a huge number, plus 4, right? It will not make any difference. That's why we drop the constants. The second rule is to only keep the highest order. What do we mean by this? Let's see an example. 7n to the power of 3 plus n plus 5. If we need to simplify this in big O, again, we are going to drop the constants, the 7 and the 5, and then we only look at the highest order, which in this case is n to the power of 3. Remember that on the other n, it's n to the power of 1, right? And 3 is greater than 1, so we only take n to the power of 3. So this will result in big O of n to the power of 3, or n cubed. Again, it's the same reason why we take the highest order. As we approach infinity, as we approach a very big number of n, only the highest order will make a difference. N to the power of 3 is massively much bigger than n to the power of 1 as we are approaching infinity. So we can drop everything else because it will hardly make any difference. So those are the two rules that you need to keep in mind when you are using this big O notation. What we will do in the remaining of this course is go through many of these functional complexity classes and discuss a problem and build a solution which belongs in that functional class. And then we will derive its runtime complexity written in the big O notation, and in this way you will learn big O notation via examples. Hello everyone, in this video we will be talking about the linear complexity class. Linear is kind of the default way that people think about scalability. When you have a task to do, if you double the amount of work that you need to do on that task, you usually also double the amount of time that you spend on it. And I'm going to make use of a very simple analogy of driving, to better explain this complexity class. Over here on my surfboard, I have two cars that are about to go for a drive. The first car sets off, drives to its first stop, which is about 100 kilometers away from the start, or 60 miles if you're American or British, and it takes it 1 hour to get there. If it continues driving to its second stop, which is another 100 kilometers away, so 200 kilometers away from the start, or 120 miles, it will take it about 2 hours to get there, 2 hours from the start. This assumes that it's still going at the same speed. This is what we mean by linear. There is a simple proportionality. If you have doubled the distance that you need to travel, you are also going to double the amount of time that you take to get there. If we had a faster car, like this red car over here, that makes the journey to the 100 kilometers mile twice as fast, meaning that it takes half an hour to get there, it will make the full journey, the one at 200 kilometers away, by spending in total 1 hour. If we had to plot this on a chart, with the x-axis having the distance and the y-axis having the time spent to get to that distance, these two would be a straight line. The red car would have a shallower curve, meaning in the same amount of time it gets further. But the fact that these two plots are straight lines, it means that they're both linear. In this analogy, these two cars are two separate algorithms doing the same thing. One of them is twice as fast as the other one, but they both belong to the same runtime complexity class. This is because complexity class tells us how well an algorithm scales, doesn't really tell us how fast or slow an algorithm performs. The fact that we have doubled the distance and we have also doubled the time, this tells you that they both are scaling proportionally, meaning that they belong to the linear complexity class. Let's now move on to the next video and discuss some algorithms that scale linearly. Hello, in this video we will look at a simple algorithm that has a runtime complexity from the linear class. In this algorithm we have an input list of numbers and we simply need to find the minimum out of these numbers. As you can imagine, the implementation is quite simple. All we need is a variable, we call it smallest, we initialize this variable to none, and then we start a loop iterating over every single item that we have in our list, and we compare each item to the smallest variable. If the smallest variable is larger than the item that we are comparing it to, or it is none, we replace the value of the smallest variable. So we start with 10, and because the smallest variable is none, we update the smallest variable with 10. Then we move on to 24, the next item. 24 is greater than 10, so we move on to the next. 3 is now smaller than the smallest variable, which has a value of 10, so we update the smallest variable to 3. And we go on like this. Next is 67, larger than 3, 21, larger than 3, 9, larger than 3, so we don't need to update. And the final is 34, also larger than 3, so we don't need to update anything. Once we have processed every single item in our input list, we just return the smallest variable value, which in this example is the value of 3. For the implementation in Python, I have created a file called findMinimum in the directory called linear. Let's start by writing our function. The function is going to be called findMinimum, accepting an input variable called items. This will be our list of numbers and we need to find the smallest one. So we start by creating this variable called smallest. This will store the smallest number once we finish with our simple algorithm, but in the beginning we initialize it to the value of none. At the end of this function we just need to return the value of this variable, so we do return smallest. In the middle we are going to start a loop to say for I in items we are just going to iterate over every single element that we have in our items list, and if the smallest variable is either none or I is less than smallest, meaning we have a smaller number than what is contained in the smallest variable, then we need to update the smallest variable. We say smallest is equal to I. And this is it. This is our very simple algorithm. Let's try it out just to test that it works. I have here the same numbers that we saw on the slides, these 7 numbers. And if we go ahead and run it, you can see over here that it gives us the result of 3, the minimum number in that list. Let's look at this algorithm in a little bit more details. As you can see over here, we have our main loop that iterates over every single item, meaning that we are doing a number of operations for each element in our items list. The operations are various. For example, we are comparing the smallest variable to none, or if I is less than smallest. We are also sometimes assigning the smallest number to the value of I. So you can see over here we are doing at least 3 or more operations for each element in our input list. If we assume that we have n items in our input list, the complexity in the worst case for this algorithm is order n. You might be wondering why I'm not writing 3n for this algorithm. After all, we're doing at least 3 different operations for each item in our input list. This is because it doesn't really matter whether we are doing 1, 2, 3, 4 or 100 operations for each element. The complexity is still the same. This is similar to the comparison that we did in the first video about the car. It doesn't matter whether you have a fast car or a small car, the scalability to the problem remains linear, remains the same. If we had to write a more efficient algorithm that just does one operation for each element, it would still belong to the same complexity class, even though in practical terms the algorithm might be faster. This is why we say that order of n is equal to order of 2n is equal to order of 4n. It doesn't really matter how many operations we are doing per element in our input list in this particular case, because it's still linear, it still belongs to the same complexity class. The scalability of whether you're doing one operation or 4, it's going to be the same. One more thing to mention about finding the minimum from a list of elements is of course that in Python we have the minimum function that is bundled in with the libraries. We can write minimum of numbers, our list of numbers, and this will give us the same result. Just because we are using this library call, it doesn't mean that suddenly our algorithm got a lot more scalable. It is still executing code that is probably going through every single item in our input list. So whether we are using a library or we're writing the algorithm ourselves, there is still a price to pay in terms of complexity. So if your algorithm is using libraries to maybe find the minimum or maximum or average, you still need to take that into consideration when you are calculating the total complexity of your algorithm. What we will do in the next video is look at a slightly more complicated example from an algorithm that belongs to the linear complexity class. Hello and welcome. In this video we will look at another algorithm that belongs to the linear complexity class. In the previous video we talked about having an input list of numbers and finding the minimum out of that number, the smallest number, and in fact there are many similar variations of that find minimum algorithm. For example, we can have the same thing, but instead of finding the smallest we find the biggest number, we call it find max. Another variation is to sum every item that we have in our list into a global summation and a global number. Another one is to find the average, similar to the sum, we just divide at the end by the total number of items that you have. And another variation is to find the first x. For example, if you want to find the first number that is bigger than 5 in your list. These are all examples of algorithms that are linear, where you are going through every single item that you have in your input and checking for a condition, whether they're bigger, smaller, or you're summing them up, or you're finding the average, or finding a particular condition about them. Let's look at a slightly different algorithm. And the next algorithm that we will look at is the string equals. I'm sure you have used this before. This is when you have two strings, for example, Pam and Jennifer, and you want to check if the two strings are exactly identical. For example, using this function, if we pass Pam, Jennifer, Isabel, or Isadore, they would both return false. However, Peter and Peter, because they are exactly the same string, our equals function would return true. Let's have a look at how we can implement this equals function. Of course, to implement this, we can use the equals operator in Python, but we are going to implement our own to understand how it works underneath. If we had to implement our own, we need to follow two rules. Let's take the example of Pam and Jennifer, two strings that are obviously not equal. And the first rule to follow is that the two strings need to be of equal length. So when we compare the length in characters of Pam and the length in characters of Jennifer, they need to be equal. In this particular example, of course, they are not equal. Pam is 3 characters and Jennifer is 8 characters. So immediately we return false. We say that Pam and Jennifer, the strings, are not equivalent. Let's pick a different example now. We have Isabel and Isadore, and they meet the first rule. Isabel is 6 characters long and Isadore is also 6 characters. The second rule to follow is that we need to make sure that for every character that we have in the first string, it's equal to every single character that we have in the second string. And to implement this, we also need a simple loop that iterates through every single character that we have in both strings and compares them. So we start from the first character, which is the letter I. It is equal, so we move on to the next. S is also equal. We move on to the next. A, again, it's equal, so we move on to the next. And now we have B and D, which are not equal. So here we fail this check and we return false. If we pick the final example of Peter and Peter in both strings, they both succeed on both rules. If we had to go through every single character that we have in both input strings, it would pass every check on each character. So in this case, we would return true. Let's now move on to the code and implement the string equals function. I have here created a file called string equal and I've placed it in the linear directory. Let's move on to write our function signature. The function is going to be called string equals, accepting two parameters, string A and string B. And now it's just a matter of implementing those two rules. If we manage to pass these two rules, we need to return true at the end, meaning that the two strings are equal. To implement the first rule, it's quite simple. We need to check whether the length of string A is equal or not to the length of string B. If it's not equal, what do? We return false. The second rule requires us to iterate over the letters in our input strings. So we need a loop to say for I in range of length of string A. This is going to give us a pointer which we can use to advance the characters on both strings. And inside this loop we say if string A at I is not equal to string B at I, it means that the characters are different. So in that case we return false. Let's quickly try this out. I have here the same 6 strings that we had in the slides: Pam, Jennifer, Isabel, Isadore, Peter and Peter. And if we run it, you can see over here that it gave false for Pam and Jennifer, false for Isabel and Isadore, and true for Peter and Peter. Notice that in the first part of our function, when we are doing rule 1, we are checking the length of string A and the length of string B. To check the length of a string, this is probably a constant operation, meaning that it doesn't matter how long the string is, it will always take the same amount of time. So this gives the impression that we should add this to our complexity. This gives the impression that the complexity of this algorithm is order n, which is our main loop, where we are iterating over every single item in our input list, plus 2. One for checking the length of string A and another one for checking the length of string B. However, we don't need to worry about this part, about the constant part. It's important to realize that in BigO notation, we drop the constant. We actually keep only the part which has the highest order. If we had, for example, n to the 2 plus n, we only take the part which says n to the 2, the most important part. This is because when you take it in balance, the n squared is much more relevant than the n by itself. And also, in a similar way, the n plus 2, the n part is a lot more relevant than the constant part. So in BigO notation, we tend to simplify everything and we drop the constants and we only keep the part of our expression which has the highest order. In this case, we say that this algorithm has a runtime complexity of order n. We forget about the constants. The other thing to think about is that this algorithm has a different best and worst time complexity. In the best case, when the strings are not of equal length, for example the Pam and Jennifer, the algorithm will return false almost immediately. It will do a constant operation of measuring the length of string A and string B, and it will return false immediately. So when the strings are not the same length, the algorithm has a constant runtime, meaning that in the best case, this algorithm has a runtime complexity of order 1. This is the way we write the constant complexity. The best case of an algorithm is very rarely used. Most of the time we only worry about the worst case. This is because it's much easier to compare the worst cases of different algorithms and also to be able to tell that even in the worst case, your algorithm will be scaling predictably. The worst case of this particular algorithm is when we have a complete match. In our example, it's the Peter and Peter, when the two strings are of the same length and every character is the same. In the worst case, we have to iterate over every single character that we have, so we do order n operations. And again, like I mentioned in the previous video, it doesn't matter whether you are writing the algorithm yourself or you are using the Python operator, the Python equals operator. String comparison between two strings will likely have a linear runtime complexity. If we had to plot the performance of this algorithm or any linear time algorithm for that matter on a graph where the x-axis is the size of our input and the y-axis is the number of operations, we would see that this is a straight line, similar to the graph that we saw when we were playing with cars in the initial video. The number of operations performed, or the time it takes, is in direct proportion with the size of our input. A faster algorithm will have a shallower gradient, whereas a slower one will have a steeper one. However, if it is a straight line, they will all belong to the linear complexity class, meaning that they have a complexity of big O of n. Hello everyone, in this video we will be talking about the quadratic class. I'm calling it quadratic class. In reality it is the quadratic function class, not the complexity class. Complexity class is something else. As usual, in order to understand this function class, I'm going to make use of an analogy. Imagine we had a frozen lake of length n, and this could be n meters or n yards, whatever your unit of measurement is, and we had someone that wanted to cross this lake. It's too dangerous to simply try to cross it because the ice might not be thick enough. In order to make the crossing safer, this guy gets a few sheets of wood that he will then use them to place on the frozen lake so that the crossing is safer. If you spread the weight on a larger area, there's less chance of the ice breaking. Now let's try to count the number of steps that this guy needs to take in order to cover a lake with different lengths. Now let's assume that all these planks are of the same length. Let's say that each of them is 1 meter in length, or 1 yard, depending on your unit of length. Let's try now to count the number of steps that this guy needs to take to cover different lengths. For a length of 1 meter or 1 yard, this guy just needs to place the plank on the ice and walk over it. So for 1 unit of length, he needs to do 1 step. He just needs to place the board and step on it. To cover 2 units, he needs to go back to the shore, grab 1 more plank, move back onto the first plank, and place the next one and move on it. This means he needs to take 3 steps. So for 2 meters, he needs to take 3 steps that we just counted, plus 1 for the initial plank to be placed. This one over here is copied from the previous step. It took us 1 step to place 1 plank, to be able to move 1 meter. So in total he needs to make 4 steps if he wants to cover a distance of 2 meters. Let's now count the steps that he needs to perform for 3 meters, and as usual he needs to go back to the shore. So 2 steps to go back to the shore, picks up the plank, then another step, 3 steps, another step, 4, and then placing the plank and stepping on it. So for 3 meters he has taken 5 steps, plus the 4 steps that he has taken before. Again, this 4 over here is the previous answer, because to cover 2 meters, we need to take 4 steps. And this gives us a total of 9 steps. Let's now count the steps for the 4 meter one. He needs 1 step back, another step back, and a step back onto the shore, picking up the plank, then 1 step forward, another one, and then the final one where he places the plank and steps on it. So for 4 steps, he needs to do 7 steps plus the 9 that he did before to cover the 3 meters. So this gives us a total of 16 steps to cover 4 meters. And we can continue counting in this fashion. For 5 meters, he needs to do 9 steps. I have counted this before, and add the 16 that we had from the 4 meters before, giving us a total of 25. For 6 meters, he needs to do 11 steps plus the 25 before, giving us a total of 36. Let's now try to find a general solution so that we can get the number of steps that he needs to perform if he needs to create this long wooden plank path of length n. Let's try to solve it for the general case. Let's first start by trying to find a pattern. So for 1 meter, if you notice over here, we had 1 step. For 2 meters, we had 4 steps. For 3 meters, we had 9, 4, 16, 5, 25, and 6, 36. Does this remind you of anything? If it doesn't, don't worry, I will explain further. So here we can rewrite this by saying 1 is equal to 1 times 1. Here, 4 is equal to 2 times 2. 9 is equal to 3 times 3. And 16 is equal, of course, to 4 times 4. You can see the pattern that's developing over here. 5 times 5 gives us 25. 6 times 6 gives us 36. And we can rewrite each one of these to say 1 squared, 2 squared, 3 squared, 4 squared, and so on, 5 and 6 squared as well. So just by observation, we can see that the number of steps that we are performing is growing quadratically with n being the length of our lake. By quadratic, I mean that is to the power of 2. So if I had to find the number of steps that I need to take in order to cross a frozen lake of 10 meters, I just need to do 10 to the power of 2, which gives me 100 steps. If we think of this manner of crossing the frozen lake as an algorithm, if we use n as the input to our algorithm, being the size of the lake, we can consider this algorithm to have a runtime complexity of order n squared. If we had to plot this on a chart, as you can see, the quadratic expression, the n squared, grows a lot faster than the linear. And this is why quadratic algorithms do not scale well compared to the linear one. In the next videos, we will come up with an algorithm that has this runtime complexity, and we will run this code with different inputs to see how it varies with the size of our input. Hello everyone and welcome. In this video we will look at a problem which we will try to solve by using a quadratic algorithm. This problem takes inspiration from the aviation world. Imagine that we were traffic controllers. Now, I'm not a traffic controller, so I'm not exactly sure what their job is, but I would imagine that a big part of their job is looking at radar screens. Let's imagine that we would want to write some tooling, or some code that would help us, the traffic controllers, with our day-to-day job. Specifically, we want to write something that would alert us whenever two planes come too close together. Our program would calculate the distances between all the points that we have on our radar, the aeroplanes, and it would find the pair that are closer together, that have the minimum distance, and it would highlight it. This problem is known as the closest pair problem. And in this problem, you are given a list of points. Now, these points can be in any dimension. Okay, we are going to keep things simple over here. We are just going to take the x and y coordinates, 2 dimensions, but in reality, you can have as many dimensions as you want. Now, this list of points will be the input to our algorithm, to our solution, and every element of this list has an index. So each point is uniquely marked. Remember that our aim is to find 2 points in our list of points that are the closest together. In this example of 5 points, the 2 points would be the 2 and the 3, these ones over here. Now, there are different solutions to this problem. What we will see over here is a quadratic solution. It is the simplest solution you can think about. We will compare every single point that we have with all the other points. So this is not the most efficient solution there is out there. In fact, it is quite slow. In the later sections of this course, we will see a more efficient solution to this problem. The algorithm that we will describe in this video requires 2 variables, the minimum distance and the closest pair. These 2 variables will be initialized, the first one to infinity, the minimum distance will be initialized to infinity, and the closest pair will be initialized to none and none. Initially, we don't know which are the closest pair, and we also don't know what is the minimum distance. Let's build this algorithm step by step, and let's start thinking about the first point that we have in our list, the point ID 0. From this position of the point at ID 0, we can try to find out the distance to every single other point that we have on the list. So the first thing we do is we go and calculate the distance to point number 1 from 0 to point number 1, and we find that the distance is 7 in this particular example. To calculate the distance, there is a mathematical formula that uses Pythagoras. We will not go into detail of what the formula is, okay? We will just use a Python function, but the formula is quite simple. You give it 2 x and y's coordinates, and it gives you the distance between them. Once we find this distance, we compare it to the minimum distance variable. If the minimum distance variable is bigger than the distance that we have just found, we need to update our variables. In this case, 7 is less than infinity, so we update the minimum distance to be 7, and we also update the closest pair variable. From none, it will be 0 and 1, because we have chosen these 2 points to be our 2 closest pair. And from that, we move on to calculate the distance between 0 and 2. Between 0 and 2 we have a distance of 5. 5 again is smaller than our current minimum distance, which is 7, so we update that 7 to be 5, and we also update our closest pair variable to be 0 and 2. We move on to point 3, the distance between 0 and 3. This gives us 6. 6 is greater than 5, so we don't need to update anything over here. The minimum distance stays 5. The distance between 0 and 4 is 11. Again, we don't need to update anything because 11 is greater than 6. And then we find the distance between 0 and 5. And now the distance is 12. 12 again is greater than our minimum distance of 5, so we don't need to update anything. Let's pause over here and move on to the code and implement this first step of our algorithm. This kind of checking from the point 0 to every other point that we have for the distances. Over here I have created a file called closest pair, and you can find this in the quadratic directory. I will be using this class called point2d to represent every single point that we have in our input. If we move on to this Python file called point2d, you can see over here this is a data class that just contains x and y coordinates. It's a simple class with these two attributes. This is just to simplify our coding. If we move back to our main class where we will implement the algorithm, let's define our function. Let's call it findClosestPair, and it will accept one parameter, the list of points that we have. This is our input of points containing the x and y coordinates. Let's create our two initial variables. The first one is called minimum distance, and we'll assign it the value of infinity. The second variable is called the closest pair, and we'll assign it the value of none and none. Now we just need to pick the first item, which is the points at position 0, and compare it to every single other point that we have in the list. And to do this, we just need a loop. So we do for j in range from 0 up to the length of our input, the length of points. And in Python, you don't need to specify this first argument. You don't need to specify these starting from 0. The default is that you start from 0. So we can remove this argument. And inside this loop, we are going to find the distance from 0 to every other point that we have in our input. So we say distance is equal to distance. This is a Python function over here. It's taken from the math package. And we say distance from point 0 to point j. In this loop, we will go through every single point that we have and compute the distance from the initial point. And then if this distance is less than our current minimum distance, we need to update our two variables. So inside this if clause, we say minimum distance is equal to distance, this new distance that we have, and then we say closest pair is equal to point 0, point j. This is not the full algorithm. All we have done over here is to find the minimum distance between point 0 and every other point. We haven't considered all of the other points that we have in our input. So let's move back to our slides. And now we need to repeat this exercise for every other point that we have in our input. So we did this comparison at point 0. If we repeat this operation at point 1, we find all of these distances. For example, the distance between 1 and 2 is 7, between 1 and 3 is 6, and so on. And every time we are finding these new distances, we keep updating the minimum distance and the closest pair. In this example over here, when we are finding the distance from the ID 1, there isn't a single distance which is less than the current minimum distance, which is 5. So we don't need to update it. We repeat again the same operation, this time from the point ID 2, this one over here, and we find the distances to all of the other points. And this time, because we have a point that is close to us, the point ID 3, which also has a distance of 3, we will update the minimum distance and the closest pair. The minimum distance is updated to 3 and the closest pair is updated to 2 and 3. And we continue with the algorithm in this fashion. We repeat the same procedure with the point at ID 3 and we find all the distances to all the other points. Then with ID 4, all the distances, and finally with ID 5. Every time we have to keep on maintaining the minimum distance variable, and the closest pair. At the end of our algorithm, we will have the solution to our problem. The closest pair in this example is 0.2 and 0.3, and the minimum distance is 3. Let's move back to our code just to finish our algorithm. In our code, we are just comparing 0.0 to everything else. We are not taking care of all the other points that we have. So what we need to do is to iterate through every point that we have and do the same thing again. So we need another loop, an outer loop if you like, that repeats this operation. So we can say for I in range of length of points, because we are going to repeat this operation for every point that we have. And we just need to move our inner loop so it's nested in the outer one. Next, we need to update the calculation of the distance, so we don't use 0.0, but instead use point at I. And we also need to update the closest pair over here. In case it changes, we need to use the point at I instead of point at 0. The other thing that we need to make sure over here is that we need to make sure that we're not comparing the distance between ourselves. If we are trying to find the distance to the same point, for example, from 0 to 0 or from 1 to 1. So here in this if statement, we just need to do an AND clause and we say I is not equal to j. We only update the minimum distance and the closest pair if I is not equal to j. This is just so we don't include the distance to ourselves. Finally, at the end of our algorithm, we just need to return the closest pair. And this is it. This is our closest pair quadratic function. I have here an example with a few points. Let's just try it out to see how it works. And if we run it, you can see over here that it gives us one solution, the solution with 2 points. What we will do in the next video is analyze this algorithm better, try to understand why it is quadratic, why it has a runtime of quadratic, and later we will look at ways of optimizing it and see if it affects its runtime performance. Hello, in this video we will examine into more detail our implementation of the find closest pair. If we look into more detail of our implementation, we can see our nested loop in here that is iterating using j over the range of all of our points. This means that if we have n points, we are executing all of these operations that we have inside this loop n times for this particular loop. Now, in addition to this, we have our outer loop that is iterating using the I variable, which means that we are executing the inner loop at least once for each point that we have. And again, if we have n points, it means we are executing the inner loop n times. This means that the instructions inside the inner loops, these ones over here, are being executed n times n times. This is why this algorithm is quadratic. We can rewrite n times n to be n squared. So we say this algorithm has a runtime complexity of order n squared. When you have these two nested loops like this, it's usually a good indication that the algorithm is quadratic. Again, it doesn't matter how many operations we do inside these loops, whether we're doing 1, 3, or 100, the algorithm still stays quadratic. This is because in BigO notation we drop the constants, so 100 n squared becomes n squared. I wanted also to give you a bit of a feel of how badly quadratic algorithms scale. And over here I have another Python file called radar window, and if we go to this file contains a bunch of code just to plot the different points on our screen. And here at the end we have our main code, which is simply generating a bunch of random points, plotting them on the screen, and then executing our algorithm. And in fact, if we scroll up, you can see over here that we are importing our find closest pair function, and over here we are calling it. So this is calling the algorithm that we have developed in the previous video. And in this first run, we can generate 400 points and try to find which 2 points are the closest. So if we go ahead and run this program, it's going to generate my 400 points. Imagine these were planes on a radar screen. And I have this little button over here that when I hit it, it's going to find me the 2 points that are the closest together. And you can see over here, it has highlighted with a red circle the 2 points that are really close together. You cannot see them very well because they're so close together, they're a couple of pixels apart. But these are the 2 planes or points that are the closest together. If we now close this and go back to our IDE, you can see also that we have recorded the time taken to compute the closest pair. It has taken less than a second. In fact, it has taken 0.133 seconds. One thing I want to do is to go back to the closest pair algorithm and remove this example over here so we don't compute it twice. Now, if I go back to our radar window Python, and instead of running it with 400 points, I run it with 4000, so 10 times more points. And I go ahead and run it. Takes a couple of seconds until it generates the 400 points. And then I hit the button, and then it's going to compute which points are the closest. Now this takes a while, so I'm going to fast forward the video so you don't have to wait. And there you go, that is the 2 closest points. Again, they're very close together. But if we close this window, we can see the time that it has taken. It has taken around 15 seconds. Let's pin this tab and try again with 8000 points. We are doubling the amount of points that we have on our radar screen. Instead of 4000, we have 8000, and we have to wait a couple of seconds until we generate around 8000 points. And when we run our closest pair algorithm, it's going to take a while because now we have a lot more points. And as usual, I'm going to fast forward the video so you don't have to wait too long. It has found again the closest pair. And let's close this window. And this time it has taken 63 seconds. So even though we have doubled the amount of points, the amount of time taken has more than doubled. It has taken about 4 times more. And again, let's pin this tab and let's run it one more time. Let's go back to our code, and this time we run it instead of 8000 points. Let's comment this line and run it instead with 16,000 points instead of 8000. So let's go ahead and run it, and as usual it's going to take a few seconds to generate the 16,000 points. Our generation algorithm also checks that there isn't a point already existing on that same X and Y coordinates. That's why it takes a little bit longer. And once it's finished, it will show me the button so I can run the algorithm to find the closest pair. So let's go ahead and press this button. And as usual, our closest pair algorithm is working to find the 2 closest points. And I'm going to fast forward. And there you go. It has finished. It has identified the 2 closest pair. I can close this window, and it has completed in 266 seconds. Again, even though we have doubled the amount of planes that we have, the time has more than doubled. It has actually quadrupled. And if we go through our tabs, the 3 runs that we have, the first one that had 4000 planes computed in 15 seconds, then we doubled the number of points that we had to 8000, and the time taken went up to 63 seconds, and then again we doubled it to 16,000, and the time took 266 seconds. I have repeated this procedure a few times more, and I have actually plotted the different values on a chart. You can see it over here. You can see if you plotted that the runtime does not scale linearly with our input size. It actually is scaling quadratically. You can see the curvature of the line. This is a quadratic curvature. If we had to plot n squared on this chart, it would have the same curvature. Another thing I wanted to show in this video is the comparison with a really badly performant linear algorithm. Over here we have a chart comparing a quadratic function, right, n squared, with a really slow linear algorithm. Over here we have the function 100n. Imagine we had an algorithm that was linear, but it had a lot of operations to perform. You can see that the line shoots up really fast. This means that even for small inputs, the time that it takes is quite long. You might be fooled in thinking that the quadratic algorithm is a better choice than the linear one. This might be true for certain values of n, for small values of n. However, as you increase the input size, the quadratic algorithm will always tend to be slower. And in fact, if we zoom out, if we try to increase the scale of our input n, right? So this has the effect of giving a larger input to our algorithm. You can see that the curvature of the quadratic function exceeds that of the linear one. And this is a very important lesson to learn. It's a recurring theme in this course, that the complexity of the algorithm does not tell us how fast or how much memory it consumes. It tells us how well it scales with regards to the input size. We can have certain linear algorithms that are worse performing with small input sizes than the quadratic one. However, when you increase the input size, the quadratic one will always scale worse in the long run when n is a large enough number. What we will do in the next video is explore an optimization on this algorithm, and then we will check whether this optimization has improved the runtime complexity of our code. Hello everyone and welcome. In this video we will look at a small optimization that we can do on our closest pair algorithm. In the previous videos we have implemented an algorithm that goes through every point that we have in our input and computes all the distances to all other points. So for example, from point 0 we would compute all the distances to all the other points. This would result in a total of 5 calculations from point 0. So we would calculate the distance from 0 to 1, 0 to 2, 3, 4 and 5, giving us a total of 5 distance calculations. When we come to point 1, we do the same amount of calculations. We calculate the distance to 0, to 2, to 3, to 4 and 5, resulting in 5 calculations. However, if you notice, the distance from 1 to 0 is the same as the distance from 0 to 1. It doesn't matter which order you calculated. So actually we don't have to calculate this twice. We have already calculated the distance from 0 to 1 when we were iterating on point 0, so we don't need to calculate the distance back. So we can omit this from the iteration at ID 1. If we adopt the rule that we only calculate the distance to the IDs that are higher than the point that we are on, we do less calculations. So for example, at point 1, we do not calculate the distance to point 0. This would result in 4 distance calculations. When we move to point 2, is the same thing. We don't need to calculate the distance to point 0 or the distance to point 1 because we have already calculated these distances when we were calculated the distance from 1 to 2 and from 0 to 2. So we don't need to calculate these 2 distances. So again, what we're doing here is that we're only calculating the distances from 2 to any ID that is higher than 2. So to 3, to 4 and to 5. This would result in a total of 3 calculations, and we continue in this fashion. At ID 3, we only calculate the distance to ID 4 and ID 5, resulting in 2 calculations. At ID 4, we only calculate the distance to 5, resulting in only 1 calculation. And at ID 5, we don't calculate anything because we have calculated everything, so we compute 0 distance calculations. This is quite an improvement over the previous algorithm because we are doing far less distance calculations. If we now move on to the code, here we have the algorithm that we have written before, the one that's called closestpair.python, the one that we have used in our radar window. And to perform the small optimizations that we have described on the slides, we just need to do a small change. In our nested loop, instead of iterating from 0 to the length of points, which is the default first attribute of the range function, we can instead do I plus 1 over here, which means we are going to start the iteration from 1 more than the ID that we are currently processing. So for example, if I is 1, we only calculate the distance to I plus 1, which is 2, and then to 3, to 4, and to 5. With this small extra change, we are greatly improving the performance of our algorithm. The second thing that we can do is to remove this AND condition. This is because I can never be j, because we are always starting from I plus 1. We are always starting from 1 more than I, so it can never be the case that j and I are the same value. So we can remove this extra condition from here. And now what we can do is go back to our radar window UI code. And if we scroll down in this page, you can see over here that we are going to generate 1000 points and find the 2 closest pairs. So let's go ahead and run it. And let's press the button to calculate the closest pair. This is the closest pair, they're very close together. And if we close this window, it's now using the optimized algorithm, and you can see that the time taken is around half a second. If we go onto the other tab, I have run this before. I was recording with the previous algorithm, with the non-optimized algorithm, and it took more than 1 second. So we have greatly increased the speed of our algorithm. Our algorithm is more performant because it's doing less distance calculations. The question that now we have to ask ourselves is whether we have changed the runtime complexity of this algorithm. We know that it is more performant, but does it scale better or not? Let's now move back to the slides to try to find out the runtime complexity of our optimized algorithm. To simplify things a little bit, instead of taking n to be the size of our input, let's take n to be the highest ID of our input. In this case, n is equal to 5. We have 6 points, but the highest ID is 5. So n will always be the size minus 1, always 1 less than the size of our input. When n equals 5, we already found all the operations or distance calculations that we need to do. These are the 5, 4, 3, 2, 1. If we count them all up together, this will give us 15 distance calculations. Let's try to figure out the number of operations that we would perform with different values of n. Remember that n is the biggest ID that we have in our input. Always size minus 1 of our input. So when n equals 5, we already saw that we get 15 distance operations. When n equals 4, which means we have 5 items in our input, to calculate the amount of distance operations that we are going to do, it will be the result of 1 plus 2 plus 3 and plus 4. And this will give us a result of 10 distance calculations. This is basically repeating that distance calculation exercise that we had on the slides, however with 1 less item, right? Instead of 6 points, we have 5. For n equals 3, so 4 items, we would do 1 plus 2 plus 3. This will give us 6. For n equals 2, meaning we have 3 items, this would just be 1 plus 2, giving us 3. And for n equals 1, meaning we have 2 items, this would be just one distance calculation. Some of you might have noticed the pattern on these numbers. If you aren't aware, these numbers are what is known as triangular numbers. And the next number in this sequence is 21. If you're wondering why they're called triangular numbers, let me quickly show you. In the first sequence, we just have 1, so we're just going to draw one shape. The next number in the sequence is 3, so we can paste this over here and then paste 2 more, giving us 3 of these circles. Now we have 6, the next item in our sequence, so we can copy all of this, paste it. We have 3 circles, and let's copy these 2 again. So we have 5 now, and let's just copy 1 more, and now we have 6. You can see the shape of a triangle forming here. Let's continue in this way. Let's copy all of these circles, put them over here. The next number in the sequence is 10, and let's just copy this layer over here, paste it, and add 1 more because we need 10 circles. Again, you can see the shape of a triangle. If you notice, each side of this triangle is of size 4 circles, 4 being equivalent to n in each one of these examples. Let's just do the last one when n equals 5, so we will have a triangle with a side of 5 circles. And let's just copy this last layer over here, move it down here, and let's just copy and paste the last circle and just tidy up a little bit. But you can see there's another triangle formed, and this time it has a side of size 5. If you want, you can continue in this fashion, try to create a triangle with 21 circles. But the important thing over here is to know how to generate this sequence. You can do it manually, every time adding the next number, right? So from 15 you add 6, then you add 7, and so on. Or you can get a formula, which I'll write over here, which is n times n plus 1 divided by 2, and then you just put n into this formula and it will give you any number of this sequence. For example, for n equals 10, so this would be when our algorithm has an input size of 11, we would get 10 multiplied by 10 plus 1 divided by 2. This would result in 110 divided by 2, which gives us 55. So the 10th number of the sequence is 55. You can create another triangle if you want with 55 circles. So going back to our algorithm, to our optimization, when the input size of our algorithm is n plus 1, we get n times n plus 1 divided by 2 operations. Does this mean that this algorithm has a better runtime complexity? Well, let's find this out. Let's simplify a little bit this formula by just multiplying the arguments on top. So n times n plus 1 gives us n squared plus n. What's happening over here is just n times n gives us n squared, and n times 1 gives us n. And of course, we still need to divide by 2. Now it's just a matter to simplify it in big O terms. And remember that when we have big O, we always drop the constants, so we don't need this divide by 2 over here, and we always take the highest order. In this case, it is the squared, the n squared. So we don't need the plus n over here. So the runtime complexity of this algorithm is order n squared, which means it will scale as bad as the non-optimized one. This doesn't mean that it's not faster, it just means that as you increase the input, it will behave similarly to an n squared algorithm. And again, this shows how the big O notation only tells you how well or badly an algorithm scales. It doesn't necessarily tell you how fast or efficient that algorithm is. Hello, in this video we will be talking about the constant functional class. In the previous videos we talked about the analogy of getting from A to B and comparing them to different functional classes. For example, we talked about using a car traveling at constant velocity and we compared it to the linear runtime complexity. Or for example, that guy crossing the lake and comparing it to the quadratic one. In this video we will use something similar by using magic and comparing it to the constant class. So imagine we had this person at position A and wanted to move at position B. And this particular person has a magic wand that can just wave around and suddenly it would disappear from position A and then reappear at position B. This particular person has a way to teleport from one position to the other. In this analogy, just like in the previous videos, the distance from A to B is the input size to our algorithm. The bigger the distance between A and B, the greater is our input size. Now, when you think about teleportation, you usually think that the process is instantly. You disappear from point A and instantly appear at point B. But in our analogy, it doesn't have to be like that. It can take a few minutes. Let's say, for example, it takes you 5 minutes to teleport, and this 5 minutes will be constant whether you are traveling 5 meters or you are traveling on the other side of the world. This is what we mean by constant time. Our algorithm will take the same amount of time irrelevant by the size of our input. The time that it takes is irrelevant as long as it is constant, as long as it doesn't vary with the input size of our algorithm. Algorithms that have a constant space or runtime complexity are the most scalable algorithms. Typically, these algorithms use some math trick to be able to achieve this constant runtime complexity. And this is why I wanted to use the magic analogy for you to remember this. What we will do in the next video is have a look at one such algorithm. Hello and welcome. In this video we shall see a problem that we will later build an algorithm slowly in various steps that will have a constant runtime complexity. The problem that I chose for this topic comes from graphs. Graphs in computer science is a very big topic. There's a lot of different algorithms and a lot of theory. However, in this section we shall see the simplest of algorithms. For those of you that are not familiar with graphs in computer science, a graph is simply a collection of nodes. These are usually drawn in a diagram as circles, and these nodes usually represent different entities, like for example cities, but they could also represent different things like families or people or objects. And the other component of a graph is what is known as an edge. An edge connects two nodes together. In this example over here, we're connecting Las Vegas with Dallas. And the graph typically contains many of these edges connecting the different nodes together. These edges usually represent connections between objects. For example, you could, in this example over here, represent the flights available between cities. For example, you can fly from Seattle to Denver. However, you cannot fly directly from Denver to Dallas. You have to take a connecting flight. Also, the edges themselves can contain information that mean something for that connection. For example, over here on each edge, I have the number of hours that you would have to drive to get from one city to the next. For example, it would take you 26 hours to drive from New York to Denver. Now, as you can see in this example, the graph is not fully connected. This means that there are at least two or more nodes that are not connected together. For example, between Seattle and New York, there is no direct connection, nor is there one between Denver and Dallas or Las Vegas and New York. Here's another example where every single node in the graph is connected with every other node. This is what is known as a fully connected graph. In this section, we want to try to come up with an algorithm that for a fully connected graph, for a graph that contains all the possible edges, containing n nodes, n being the total number of nodes in that graph, we need to find e, the total number of edges in that fully connected graph. For example, for n equals 5, meaning a graph with 5 nodes, in our previous example we had 5 American cities, we should return the count of 10 different edges to produce a graph which is fully connected. If you had to count every edge in this graph, you would have a total of 10 edges. Let's have a look at how we could try to solve this problem. A simple approach would be to go from each node in our graph, in this example we have cities, and try to connect to every other nodes where there isn't a connection yet. So from Seattle, we would connect to New York, then to Denver, then to Dallas, then to Las Vegas. So we already have 4 edges over here. Every time we have a new edge, we add 1 to our counter. And then we move on to the next node, which is New York, and we connect the remaining. So we connect to Denver, we add another edge to the total count. We connect to Las Vegas, again always adding another edge to our count, and then we connect to Dallas. Then we move to Denver and we add 2 edges to Las Vegas and to Dallas. And then we go to Las Vegas and we add another edge to Dallas. Once we go to our final node, the node to Dallas, all the edges are already there. All the outbound edges from Dallas are already defined, so we don't need to add any other edge. Let's move on to the code to implement this very simple basic algorithm, the one to count the total number of edges. Over here I have created a file called total edges quad found in the constant folder. Let's go ahead and write our function signature. The function is going to be called number of edges, accepting the total number of nodes. This is our input. This is an integer containing the total number of nodes that we have in our graph. So for example, if we feed 5 to this algorithm, it should return 10. Inside the implementation, we are going to initialize a variable called result and give it the value of 0. And then at the end, we are just going to return this result. Now we are going to start a loop to iterate over every node that we have. So we say for I in range of nodes. Remember that nodes is just an integer, giving us the total number of nodes that we have. So in this loop, if, for example, the total number of nodes is equal to 5, this loop would result in I having the values of 0 up to 4, inclusive. So this outer loop is simulating us iterating over all the nodes that we have. We are iterating 5 times starting from 0. Inside we are going to create a nested loop, and this time we say for j starting from I plus 1 up to nodes. This means we are always going to iterate 1 less than I. In order to understand this, let's try to step this through. So when I is equal to 0, the range of j is going to be from 1, so 0 plus 1, so 1, up to 4. Remember that nodes is 5, And we stop one less because this is an exclusive loop, right? In Python, the range stops one less. So j is going to have the value of 1, 2, 3, and 4. Then when I is equal to 1, we are going to iterate from 2 to 4 because we are always doing I plus 1. And then when we have I is equal to 2, we are going to iterate from 3 to 4. And then when I is 3, we are going to iterate from 4 to 4. So we only iterate once. And then when I is 4, we are going to iterate from 5 to 4, which means we are not going to iterate at all. This is kind of simulating creating all of those edges that we saw on the diagram. Starting from the first node and then moving on to the second node and creating one less edge each time. When we get to the last node, when I is 4, there are no more edges to add. So inside this nested loop, we just need to count. We just need to do result plus equals 1. And if we had to work this out from 0 to 4, this will give us a plus result of 4. Next one will give us a plus result of 3, right, from 2 to 4. And then we will have a plus result of 2. And after that, a plus result of 1. And then the final one will be 0. We will not add anything. And if we add all of these up, we will get the result of 10. Let's tidy up and then try it out with a few examples. Over here, I have a number of examples starting from 1 up to 6. I'm trying out this new function with graphs having the size from 1 up to 6. And if we go ahead and run it, you can see over here that it gives us the correct results. A fully connected graph of one node, of course, doesn't have any edge. That's why you see 0 over here. But also when the number of nodes are 5, you get the result of 10, just as the example that we saw on the slide. If we go back to our algorithm, let's try to examine to see what is the runtime complexity of our simple function over here. And just like we saw in the quadratic section, it's easy to see that we have these two nested loops, both iterating over the size of our input. This gives us a runtime complexity of order n squared. So this algorithm is quadratic. If we kept on increasing the size of our input, our algorithm will slow down quadratically, will not scale very well. What we will do in the next section is change this algorithm to first give us a linear runtime complexity, and later we will improve it by using a match trick to have a constant runtime complexity. Hello, in this video we will improve the previous algorithm, the one we developed that had a quadratic runtime complexity, and we will first write a linear complexity version and then we will write a constant one. Over here I have the same graph that we had in previous video, the one with the different cities, and we want to fully connect them with all the possible edges and count the total number of edges that we had. In the previous algorithm we were counting each edge separately, one at a time. However, there is a bit of an improvement in that we can count all the edges coming out from one node. So if we start from the first node, Seattle over here, we can count all the edges coming out to all the other nodes, which in this case it's 4, right? One to New York, one to Denver, to Dallas, and to Las Vegas. This will give us 4, and we can use that number and add it to our final result. So instead of counting each edge at a time, we simply add 4 to our result variable. Then we move on to the next node, which in this example is New York, and this time we have 3 edges. So we add 3 to our result variable. And then we move on to Denver and we add 2 edges. And after that to Las Vegas, adding 1 edge to Dallas, and then from Dallas adding 0 edges. As you can see over here, the pattern is simply adding 4, 3, 2, 1, and then 0. So we start from 1 less than the total edges that we have and go down all the way to 0. Over here I have our previous algorithm, the one that had a quadratic runtime complexity. I have simply copied it to a file called total edges linear in the constant directory. If we remove our nested inner loop, so we don't have to count each edge one at a time, instead we can replace it by counting the total number of edges that we have outgoing from each node. We just need to do nodes minus I plus 1. Remember that nodes is the total number of nodes that we have in our graph. So we are always counting one less than the node that we are processing. If we had to take a concrete example with a graph of a total of 5 nodes, in this outer loop we are iterating from 0 up to 4. 4 is inclusive, right? So we iterate I is 0, I is 1, I is 2, 3, and 4. And when I is 0, this expression evaluates into 5 minus 1. 5 is the total number of nodes that we have, and minus 1 because we do I plus 1. Remember that I is 0, so plus 1 is obviously 1, and we subtract that from the nodes variable. When I is 1, we just do 5 minus 2, and when I is 2, we just do 5 minus 3, and we continue in this fashion. When I is 3, we do 5 minus 4, and then finally when I is 4, we do 5 minus 5. This means that when we add the output of this expression to our result variable by doing result plus equals, we will be adding the values of 4 when I is 0, then when I is 1 we add 3, then when I is 2 we add 2, when I is 3 we add 1, and then finally we add 0 when I is 4, giving us a total of 10. Like this we are adding all the edges in one go for each node that we have. And if we go ahead and try it with the same examples, we get the same results. Again, over here, when the total number of edges is 5, we get the result of 10. If we go back to our algorithm, remember that we are iterating over the total number of nodes that we have. So from 0 to n, actually stopping one less than n. And for each node, we are doing the same amount of operations. We are doing a constant number of operations. So this gives us a linear runtime complexity. We say this algorithm is order n. Can we do any better? Can we come up with an algorithm that gives us a completely constant runtime? Let's try to think of a few examples of fully connected graphs to see if we can find a pattern in the numbers. So when we have a graph with just one node, there are no edges to connect this one node to any other nodes because there's only one, so the total number of edges is 0. When we have two nodes, there can only be one edge, right? There's only one way to connect two nodes together, so the total number of edges is 1. Between 3 nodes, we get 3 edges. And between 4 nodes, you get 6 edges. And then with 5, we already saw this in the previous example, you get 10 edges. You can also try this yourself, come up with the total number of edges for the next one, which is 6 nodes, and see how many edges you get. If we had to do this exercise and continue drawing these graphs and find out how many edges we can form, we would form this pattern, this sequence of numbers. Each one of this number represents the total number of edges that we get in that graph. When we talked about optimizing finding the closest pair, this sequence might look familiar. In fact, again, this is a sequence for the triangular numbers. And actually, to generate any number of the sequence, we can use the same expression that we saw in the previous section, the x times x plus 1 division by 2. This x over here represents the index of the sequence, right, starting from 0. So if we want the 5th element in our sequence, we would have to put x equals 4, we put 4 in this formula, and it will give us 10. However, what we need is the sequence shifted 1 to the left. This is because our input, the total number of nodes, starts from 1. When the total number of nodes that we have in our graph is 1, there will be 0 edges. When it's 2, there will be 1 edge. When it's 3, there's 3 edges. When it's 4, it's 6, and so on. We saw the 5 before in our example. When it's 5, it gives us 10. So what we need to do is simply replace x by n minus 1. This will simply shift the sequence to where we want it to be. We can easily do this, right? So instead of x, here we put n minus 1, and instead of x plus 1, we put n minus 1 plus 1. These two cancel each other, and we get n minus 1 times n. And we can simply switch around this order and make it divided by 2 giving us n times n minus 1 divided by 2. This expression will give us the total number of edges that we need in a fully connected graph of n nodes. And now we have a way to give us the answer without having to iterate over anything in our input. And in fact, we can go back to our code. I have here created a new class called totalEdgesConstant. So we just need to write this function inside our function, the total number of edges function. Let me write down our expression, the one from the slides. It's n multiplied by n minus 1 divided by 2. So in the body of our function, we just need to do nodes multiplied by nodes minus 1. Remember that nodes is our n variable over here. And then we do divided by 2. And we must remember to return this result. Let's go ahead and run it just to see it giving us the correct results, as you can see over here. And now if we go back to our implementation, you can see that our function does not really depend on the size of our input. This is a constant operation. No matter what the size of our input, no matter the size of our nodes variable, it will always return in the same amount of time. If we count over here the number of operations, we are doing 3 operations, a multiplication, a subtraction, and a division. However, this does not really matter, right? Because in BigO notation, we drop the constants, so we drop the 3, and we say that this algorithm has a runtime complexity of order 1, or a constant runtime complexity. Hello, in this video we will talk about algorithms belonging to the exponential complexity class. In order for us to understand how quickly an exponential curve grows, I am going to make use of an old fable. There was once a king that grew bored of his daily routine, and he wanted a new game that he could play with his friends. An inventor came along and came up with the game of chess. This is the chess as we know it today, the one with an 8x8 chessboard. Apparently the king was so happy with this game and he was having so much fun, he understood the rules very quickly, and he wanted to reward the inventor of this chess game with something. So he asked him for anything that he wanted. He could choose anything that he wanted and the king will make sure to give it to him. This inventor asked for a very simple thing. He wanted rice to feed his family. He asked for the king to give him the equivalent of rice if one had to put a single grain of rice on the first square of the chessboard. Then you double it and you put 2 grains of rice on the second one, and then you put 4 on the third one, and so on. So on the 4th box you would put 8 grains of rice. After that you would put 16 grains of rice on the 5th box, then 32, 64, 128, 256, 512, and so on until you fill the entire chessboard. Always doubling the amount of rice per box that you have on the chessboard. The king was really happy because he thought he got this amazing game for just a few grains of rice, and he promised this inventor to get his rice. Unfortunately, what the king didn't know is that by the time you get to the 64th box of our chessboard, you get into an astronomical number, an absolutely huge number. The amount of rice that the king would have to give him just on this last square is equivalent to around 368 billion tons of rice. To put this in context, the entire world consumes around 500 million of tons of rice every year. The fable finishes by the king getting really angry and eventually ordering the inventor of chess to death. So it didn't really work out very well for the inventor of chess. But this is a simple story just to explain how quickly exponential curves can grow. If you don't believe me, you can try to work this out yourself. You can try keep on multiplying the number of rice by 2 on each square until you get to the 64th square, and you'll see you'll get to that number. There is a quicker way to work out the exponential value at a particular point in time. If the king knew about this, he wouldn't have fallen into this trap, and this is by using simple maths. We can start by 1 and multiply it on each time, so 1, 2, 4, 8, 16, and so on, and we do it 64 times until we get to that huge number. Or we can simply use powers. We number each box in our chessboard from 0 up to 63, Remember there's 64 boxes. If we start from 0, we have 63 on the final box. And to work out how many grains of rice we need to put on each box, we can go directly. We don't need to work one after the other. Let's try to reason how to come up with this simple expression. Remember, we start from 1 and then we multiply that by 2, so 1 times 2. Then we have the previous result, which is 2, times 2 again. And then we have the previous result, which is 4. And 4 is also 2 times 2, so we have 2 times 2 times 2. And to get to 16, we have the 8, the previous result, which is 2 times 2 times 2, and we multiply it by another 2. And for all of this, we can use the expression 2 to the power of n to give us the result. So to give us the position at box number 0, we do 2 to the power of 0, which gives us 1. 2 to the power of 1 gives us 2. To get the value on position 2, we do 2 to the power of 2, which is essentially saying 2 times 2, giving us 4. Then we have 2 to the power of 3, giving us 8, which is 2 times 2 times 2. And then we have 2 to the power of 4, giving us 16. And so on, we can find the value of any box on the chessboard. And if we have to work out the final number, we do 2 to the power of 63, and it gives us this huge number. In this section, we will describe algorithms that have a runtime or a spacetime complexity of order c to the n. N is the input size of our algorithm, and c is a constant. In the previous example of the chessboard, c was 2, and n was the number of the box that we wanted to find how many rice we had on that box. We can compare this exponential class with other classes. In this graph, you see the comparison with quadratic, which is this one over here, and linear, which is this green one over here. You can see that the exponential graph grows much faster than the quadratic one. This chart is very typical when you are comparing the different complexity classes, and in fact you can find many similar charts online if you just Google it. However, it's not showing the complete picture. You might be fooled in thinking that the exponential class is slightly worse than the quadratic one. This is wrong. The exponential curve grows much faster than the quadratic one. If you notice in this chart, the x-axis, the size of our input, this chart stops at around n equals 5. If we zoom out and increase the input size just to slightly over 10, you can see how much faster the exponential curve grows compared to both the linear and the quadratic. Even with an input size of size 20, the problem typically has already become too huge for your computer to handle, either in terms of memory or in terms of runtime. And in this chart, you can also see that even when the input size is just around 20, there is no comparison with the exponential and the quadratic. The quadratic curve on this chart looks like a straight line because it's being squashed by the exponential curve. In the next video, we will discuss and implement an algorithm that belongs in this complexity class, the exponential complexity class. Hello everyone, in this video we will see an algorithm that belongs to this exponential complexity class. In this exponential complexity class there are many problems for which we don't know if there is a faster algorithm than the exponential one. Probably the most famous problem in this area is the traveling salesman problem. This is when you have this traveling salesman that wants to visit a number of cities exactly once and wants to find the route that is the shortest distance through all of these cities. Another famous problem in this area is the Hamiltonian path. This is when you want to find a path through your graph that visits each node exactly once. The problem that we will examine in this section is called the subset problem. Let's have a look at more details of this problem. In this subset sum problem, we have an input set containing a number of integers, and as a second parameter we also have a target value. We need to find a subset in our input set that when you sum it all together gives us this target value. Our algorithm needs to return true or false. If it finds a subset that when you add it up gives us the target value, it returns true. Otherwise, if it cannot find one, it returns false. A subset is simply a choice of these elements together. For example, we might choose the number 2, number 11, and the 5. If we add these three together, they give us 18. So 18 is not equal to 14, so this is not a valid subset sum that gives us this target value. We can try another subset, the 7 and the 3. This gives us 10. Again, this is not equal to 14. However, this subset over here, the 7, 2, and 5, gives us the exact number of 14. So in this particular example, the algorithm should return true, because we have found a subset that when you add it together gives us 14. If we take another instance of this problem where we have the target value of 6, you cannot find any subset in this input set that when you add them together it gives you 6. No matter what you try, it will not sum up to 6. So in this particular instance, we should return false, because there isn't a subset sum that gives us 6. Let's now have a look at how we can implement this algorithm. And I'm going to choose a small input subset of just 3 elements, otherwise the problem would become too big and I wouldn't be able to fit it on one slide. The idea of what we could implement is to go through every single possible subset of our input and sum it together to see if it matches the target value or not. So in this particular input of the set 7, 2, and 3, we would start by not choosing any of those elements. This will give us a valid subset, the subset of empty elements without any choice. The next subset that we choose is the one where we choose 7. So we have a subset with just 7 inside. Then we choose the element 2, so we have a subset with 2. Then we choose the 7 and 2. Then we choose the 3. And then we choose the first and the third, right? So the 7 and the 3 together. Then the 2 and the 3 together. Then all of them together, giving us the 7, 2, and 3 as a subset. Now it's just a matter of summing each subset up and finding out if it matches to our target value. In this example, we have the target value of 9. And if we produce the sum of all of these subsets, we get these following results. And as you can see here, the 7 and the 2 sum up to give us the target value of 9. So in this particular instance of the problem, we should return true. Generating all possible subsets from our input set is what is known as the power set. There are different techniques on how you can do this. The most famous one is to use recursion, but we are going to try a different approach over here. Maybe for those of you that are not familiar with recursion, this approach will be a bit simpler. Have you noticed the pattern at which we select our elements from our input set to generate the subset? If not, let's have a look at a larger example, one with an input of 4 values, and try to recognize this pattern. We first don't choose anything from our input set, then we choose the first one, then the second one, the first and the second, the third, first and third, second, first, second, third, fourth, first and fourth, second and fourth, first, second and fourth, then we have third and fourth, first, third, fourth, second, third, fourth, and finally all of them together. Does this remind you of anything? If it doesn't remind you of anything, don't worry. This is very similar to the way we count in binary. However, it is mirrored, okay? And over here I have mirrored all of our inputs, right? The 11, 3, 2, and 7. I have simply reversed the list, and we have a 4-bit binary number. And if we count by 1 on this binary number, it will give us a similar pattern of choosing from this subset. So when we have 1, we have the first item in our set, then 2 gives us the second item, then 3 gives us the first and the second, 4 gives us the third item, 5 the first and the third item, 6 gives us the second and the third item, and so on. 7 gives us the first 3, 8 gives us the fourth, then 9, 10, 11, 12, 13, 14, and 15, where we choose all the numbers together. If we go back to our simple example, the one with just 3 inputs, and if we use this technique with binary counting of just 3 bits this time instead of 4, we can start with the empty set because we have all zeros, we haven't chosen any of our input. Then we choose the first one because we have the binary bit of 1 underneath the 7, giving us the subset of 7. Then we choose the second one, which gives us the subset of 2. then we choose the first and the second one because we have the binary 1 under the 7 and the 2, and so on. We choose the third item, which gives us a number 3. Then we choose the first and the third item, 7 and 3. Then we have the binary equivalent number of 6, which gives us the 2 and the 3, because we have 1 and 1 underneath the 3 and the 2. And then when we have 7, we choose everything together, because 7 in binary is 1, 1 and 1. So we have 7, 2 and 3 all chosen. So we can use this binary technique to tell us which elements we need to choose in the next subset. If we go into more detail of the algorithm, we need an outer loop that uses I starting from 0 until 2 to the power of n. This is an exclusive loop, so we stop 1 less than 2 to the power of n. This I will represent this binary number over here, the one that will tell us which numbers we should choose from our input set. The reason we are doing 2 to the n is because this will give us enough space for our entire input. In this example where we have 3 digits, n is the size of our input, so n will be 3. 2 to the 3 is 8, and since we stop at 1 position before, giving us 7, this will be equivalent to 1, 1, 1 in binary format when we convert 7 into binary. We start from 0, then it becomes 1. Notice how the binary number here is changing. Then it becomes 2, 3, 4, 5, and so on. And on each iteration, we need to choose the elements that are present on these markers, on this 1-digit marker. And to implement that way of choosing, we can have an internal nested loop using j from 0 up to n. Remember that n is exclusive, so we stop at n minus 1. And we compute 2 to the power of j. This gives us another binary number that lets us apply a mask on I. So when we start this loop, j is equal to 0. This gives us 1, right? Because 2 to the power of 0 is 1. And this is the equivalent binary of 0, 0, 1. And then when j is equal to 1, 2 to the power of 1 is 2. And this has the effect of moving this binary digit of 1 forward 1 space. When j is 2, 2 to the power of 3 is 4, and this has the effect again of moving this 1 digit forward. If we had 4 digits over here in our input, j would become 3, 2 to the power of 3 is 8, and the digit would move 1 forward again. The reason why we do this digit movement is because we want to pass these two numbers into a Boolean AND gate, and depending on the result of this, we decide whether we choose this number or not. Let's work through one simple example. When j is 0, 2 to the power of j is 1. Over here, you can see that the 1 and 1 are on top of each other, and if we do 5 and 1, this gives us a non-zero answer. So in that case, we should choose that number. We should choose the number at position j. Remember, j is 0, so we should choose the number 7 in our subset. We increment j by 1. 2 to the power of 1 gives us 2, so this binary digit has moved forward. However, 5 and 2, when we AND it together, it gives us the result of 0, which means that we should not choose the number at position j. This one over here, which is j at position 1, which is number 2. We increment j by 1, giving us 2. 2 to the power of 2 is 4. This has the effect of putting the binary digit under the last element. And if we do 5 and 4, this gives us a non-zero, which means we should choose the number at position j, which is the 3 over here. So our subset is the 3 and the 7 in this particular iteration. What's left to do now is to add this subset together and check if it gives us the same result as our target input. This is basically the algorithm that we want to implement, and we shall do this in the next video. Hello everyone, in this video we will implement the subset sum algorithm. I have created a Python file over here called subset sum, and I have placed it in the exponential folder. Let's start by writing our function signature. Let's call it subset sum, and this function will accept two parameters, the parameter s and the parameter target. The parameter s is our input set, and the target is our target sum that we need to try to find in our input set. This function by default will return false, saying that it hasn't found a subset that can sum up to the target. if we do find a subset sum that is equal to the target, we will return true in the middle of this function. Let's start by finding out the length of s. So we do n is equal length of s, and then we will create the outer loop, the one we have explained in the slide, the outer loop using I. So we say for I in range of 2 to the power of n. Remember that this is an exclusive loop, so the last value of I will be 2 to the power of n minus 1. And then inside this loop, we will create a variable called sum with a value of 0. This will be the variable that will store the sum of this subset that we are trying to generate. Let's now write the nested loop, just as we have explained in the slides as well, and we will use the j variable in range of n. Inside this nested loop, we need to call this Boolean AND operator between I and 2 to the power of j. Again, just as we have explained in this slide. So we can implement this with an if statement to say if I Boolean AND 2 to the power of j, this means that we should include the number at position j in our subset. So in this algorithm, we are just going to print it out. So we say print s at j. And I am going to include a space after it, so we have a separator, and then say and is equal to empty string. This is so the elements of the same subset end up on the same line. And before we print it, let's add it to our sum variable. We say sum plus equals sum at j. Once we are done with the nested loop, we have the entire subset, and we need to check if the sum is equal to the target. If it is equal to the target, we should return true because we have found our subset sum. And this is it. This is our algorithm. I'm going to add another print over here, printing the open square brackets. This is just so we can print all the different subsets on different lines. And after the loop, I am going to print the close brackets and say sum is equal to and output the sum variable. This is just so we know what's going on in our algorithm. Over here, I have two examples. The first example has an input set of 6 elements and the target sum of 14. Let's go ahead and run it. And as you can see over here, it started generating all the different subsets. It started from the subset of 0 element with a sum of 0, then the subset with just 2, sum of 2, and so on. When it came to the subset containing the 2, 5, and 7, which has a sum of 14, it has found our subset that sums up to 14, and it has returned true. It has stopped computing. If we run this second example, the one where we are trying to find a subset sum of a total of 6, as you can see, it has returned false over here, and it has generated all the possible subsets. There are quite a few of these subsets. None of them sum up to the value of 6. If we go back to our algorithm, you can see why this is an exponential algorithm. The outer loop iterates at the worst case 2 to the power of n. Remember that n is the size of our input set. And in fact, if we try an input size that is quite large, the algorithm might take a very long time to compute. Notice also that because of our inner loop that we are executing n times for every iteration, this algorithm is slightly worse than exponential. It is 2 to the power of n multiplied by n, because on each iteration we are doing n operations. Looking at the worst and best case of this algorithm, the best case is when we give it an input target of 0. This is because it's going to match it with the empty subset. If we give it a target of 0, the first set that it will generate is the empty one, and it will return immediately, no matter how large our input set is. The worst case of this algorithm is when the function returns false. It is when we give it a target for which there doesn't exist a subset that sums to that target. This is because it has to go through all of the combinations of subsets to figure this out. And for this reason, we say that in the worst case, this algorithm has a complexity of 2 to the power of n times n. Hello everyone and welcome. In this video we will be talking about the logarithmic functional class. In the previous video, we talked about that story where we had this chessboard and we were putting a grain of rice on the first box in this checkboard, and then we kept on doubling the amount of rice that we put on each box. At a certain point, the count got so big, the amount of rice that we would put on the box got so big that it exceeded the amount of rice that is available in the entire world. We could find out how much rice to put on each box by using a simple formula. The 2 to the power of x gives us the count of rice that we need to put on each box, starting from 0 up to 63 for the last box. So for example, if we needed to find the 23rd box, we just do 2 to the power of 23 and it gives us about 8 million grains of rice just on that box. Now what if we reversed the problem? What if we say we have this count of rice grains and we want to find which box it belongs to? In maths terms, this would mean 2 to the power of x is equal to the number of rice that we have. For example, let's say we have about 131,000 grains of rice and we want to find out which box that rice belongs to. We could try to do this with trial and error. For example, 2 to the power of 15 gives us about 32,000 grains of rice, 2 to the power of 16 gives us 65,000, and 2 to the power of 17 gives us exactly the number that we're looking for. But there is a simpler way, and this involves using the logarithms. We can flip the expression around to say x is equal to log 2 base 2 of the number that we're looking for. In this example, 131,000. Logarithms are the inverse of exponential. And let me show you an example of how to work out logarithms with a special calculator. I'm using this special calculator over here because it allows me to specify the base of a logarithm. So if I go on alpha and I choose this button over here, it comes up with a menu. I choose function and I'm going to press 5, which tells me log 2 base. Press 5 over here and now it gives me the logarithm function. And I'm going to specify I want base of 2 and I'm going to specify the same number that we had on the slides, the 131,072. And if I press enter, this will give me the logarithm of 17, which is the same result that we have found out by working out the different exponentials. But basically the thing to remember is that logarithms are the inverse of exponential. And with the expression of b to the power of x gives us a, if we invert this to find x, we say x is equal to log 2 base b of a. And just to show you another example, if we have 10 to the power of x giving us 1 million, the way to find x is by doing log 2 base 10 of 1 million. And for this we can use the normal Windows calculator. We can put 1 million over here, 1 and 6 0, and then we press the log button. When there is no base specified on the log function, it means that it's using log 2 base 10. And log 2 base 10 of 1 million gives us 6. And just to give you that little bit of extra knowledge about logarithms, if you have log 2 base b of a, this can be worked out by doing log of base 10 of a divided by log of base 10 to b. So if you don't have a special calculator that allows you to specify the different base, you can use this formula to work out any base that you want. And in fact, let's repeat this exercise of finding the log 2 base 2 of 131,000. Remember that this should give us 17. By doing log of 131,000 divided by log of base 2. And this time, because we are using log 2 base 10, we don't need a special calculator, we can just use the Windows one. So in here, I can do 131,072. I do log 2 base 10, and it gives us this number. Then I do divided by 2, and I find out the log of 2. Which gives us this number, and then if I do the division by pressing enter, it will give us the result of 17. You can see the full expression over here. This is just for you to know some general information about logarithms. This is not strictly needed for this course. What is needed is for you to recognize which algorithm is logarithm and which is not. The thing that is important to realize is that the log function is kind of a squashing function. Unlike the exponential, where you give it a small number and it gives you a huge result, the log function will take in a huge input and squash it down to a small one. We saw this when we were doing log to base 2 of 131,000, which gave us 17, but there are other examples. For example, this number over here, this huge number, if you do log to base 2 of it, it will just give you 63. This happens to be the amount of rice that you can put on the last box of your chessboard. So you can imagine what this means for our algorithms. Logarithmic runtime complexity algorithms can take in a huge input and only perform a handful of steps to compute the results. This makes them extremely scalable. What we will do in the next section is look at an example which has a logarithmic runtime complexity and then implement it. Hello and welcome. In this video we will examine a problem that can be solved in logarithmic time. This problem is about finding an item in a list of elements. So over here, for example, we have a list of names, different names of different people, and the requirement to this problem is that the items in this list are ordered. In this example over here, the names are ordered alphabetically, right? So Bob comes before Isabel, Isabel comes before James, and so on, because alphabetically Bob is before Isabel. This list of items can be anything that can be ordered. So for example, it can be numbers or floating point numbers or even colors. For example, if you use the hexadecimal value of a color, but basically anything that has an order. And each item in this list has an associated index with each item. Bob is the first in this list, so it has an index of 0. Isabel is the second item in this list, so it has an index number of 1, and so on until Zoe, which has the index number of 8. In this example, we have 9 elements in our list, so the last index is number 8 if we start from 0. In this problem, what we have is an input name. In this example, we have the name Rose, and we want to know whether this name is in the list or not. And actually, we also want to return the index where this name is if it exists. So as a solution to this problem, we would return the number 5. Because Rose is on index number 5 in this input list. Just remember that the elements of this list can be different data types, like numbers, for example, or other objects, as long as they can be ordered. One simple way of implementing this algorithm to search for an item in this list is to start a pointer from the first position, from position number 0, in this case it's Bob, and we compare it to the item that we're looking for. If it's not what we are searching for, we move on to the next. In this case, we move on to Isabel. Again, it's not what we're looking for, so we move forward one more, we keep on moving forward until we match with our input. In this case, Rose is at index position number 5, so we have our match, so we return the index 5. If our input list has a size of n elements, in this case n equals 9, this particular algorithm will have a linear runtime complexity order n. If we had to be a little bit more precise for this particular data type, if we are comparing strings, the actual runtime complexity is not strictly speaking n. This is because the runtime also depends on the length of our input string. In this case, Rose has a length of 4, right? So if we assign m to be the variable of our input string length, the strict runtime complexity would be n times m, because at each element that we are searching, we are doing a string comparison. However, just to simplify things, imagine that the comparison is done in a constant manner, assuming, for example, we have a constant length of strings, or we are using numbers instead of names. With that assumption, this particular algorithm, the one where we are iterating over every single item, would have a linear runtime complexity. Can we do any better? Can we come up with an algorithm that is faster than linear? It turns out that we can, and there is an algorithm called binary search that makes use of various pointers to be able to search more efficiently. Think, for example, when you are searching in a dictionary, you don't go about searching every single word that you have in the dictionary. Instead, you open it in the middle, you try to compare the word that you're searching for, and you move back and forth depending on where you are searching. If you had to search for every single word that you have, it would take you a very long time. So the binary search mimics this kind of searching in a dictionary for a particular word. It works by using a start pointer, which initially we assign it to the first item in our list. So initially the start pointer is on index position 0, and an end pointer, which we assign it to the last position in our list. In this example, the index position 8. And we also need a middle pointer. This would be a pointer pointing to the middle of our data, the middle between the start and the end. We find out where we should put this middle pointer by doing start plus end division by 2. It's basically a simple math formula to calculate where the middle between the start and the end is. Once we have the positions of these 3 pointers, what we do is find out whether the item pointed at by the middle pointer, this one over here, the item Peter, whether it is the same as our input string. The input string in our example is rows. We are looking for rows in our input string. It's not the same, obviously, so what we do is we compare to see whether it's bigger or smaller. Rows is alphabetically later than Peter, so what we do is we move the start pointer to be the middle pointer plus 1. So in this example, the start pointer moves to the position 5, 1 position later than the middle pointer. After that, we recalculate where the middle pointer should be. Remember that the middle pointer should point in between the start and the end. Now we can put it both on 6 or 7, it doesn't really matter. If we calculate this formula over here, start plus end division by 2, it will give us 6.5, so we can round down or round up. The algorithm will still work. In this example, I decided to round down. We put it on 6. And again, we repeat what we did before. We compare the item at position 6, which is Sam, to rows. They're not the same, so we haven't found what we're looking for. So we know that rows is alphabetically before Sam. So this time we move the end pointer to 1 position before the middle one. So we move end to position 5. Both start and end pointer are pointing to the same location. Again, we calculate the middle pointer. The middle pointer between 5 and 5 is of course 5, right? If we do 5 plus 5 division by 2 results in 5. And again, we do the comparison. We say, is the input string rows the same as the item at index position 5? Which it is. In this case, we have rows over here as well. So in this case, we simply return the index position 5, showing that we have found the item that we're looking for. If we were looking for a different item, for example, if we were looking for root instead of rows, we would continue this algorithm by comparing rows with root. We know that root is later than rows alphabetically, so we would move the start to a position later than the middle one. So start would move to the position 6. And when we have this condition, when we have the start pointer after the end pointer, it is a stopping condition for us to know that we haven't found what we're looking for. It means that the item is not contained in our list. So this condition over here, start greater than end, means that the item that we're looking for is not in our list. And in that case, we could return the value -1 to show that the item is not present in our input list. The runtime complexity of this binary search is order log n. We say the runtime complexity is logarithmic. We will explain in detail in the next video why the algorithm is logarithmic, but first let's go ahead and move on to the code and implement this binary search algorithm. Over here I have created a Python file called binary search, and you can find this file in the logarithmic directory. Let's move on to the code and let's start by writing our function signature. It will be called binary search, accepting 2 input parameters. The first input parameter, which I call items over here, is our list of items that we want to search in. And the second parameter, which I name x over here, is what I want to search for. This binary search function will search for x inside items. We can start immediately by writing return -1. This is the case when we haven't found x in our list of items. And now let's define some variables. We need the start position, which initially this pointer will be pointing to the first item, so we will assign it the value of 0, the first index in our list of items, and then we have another variable called end, and this will be the pointer to the end of our list of items. So we do length of items minus 1. We stop on the index of the last item in our list. Now we need a stopping condition, so we stop searching if we haven't found the item. If you recall from the slides, the stopping condition is when the start is greater than the end pointer. This means that we haven't found X inside the items. So we can use an if statement, or we can flip this around and use a while loop. We say while start is less or equal to end, then we are going to continue this loop. This is just the reverse of the stopping condition that we saw in the slides. Inside this loop, we find the middle pointer. We say mid is equal to start plus end divided by 2. And over here I am rounding down. So for example, if I have 13 divided by 2, it will give us 6 because I am rounding down from 6.5. And now we just need to take care of the different three conditions that we have inside this while loop. If X is greater than items at position mid, meaning that the item that we're looking for is after the middle pointer, what do? We move the start pointer. Just as we have explained in the slides, we move it one position more than where the middle pointer is. We do start is equal to mid plus 1. Otherwise, if X is less than items at mid, this means that the item that we're looking for is before the middle pointer, so we move the end pointer one position before the mid pointer. We say end is equal to mid minus 1. And finally, the final condition is when X is neither greater nor smaller than the item at position mid. This means that X is exactly the same as the item at the middle pointer, and in this case we just return the middle pointer. We say return mid. And this is the full implementation. I have here a few examples. This is the list that we had on the slides, the one with 9 names. And in our first example, we are going to look for rows, the same that we had in the slides. Then we are going to look for James, which is at position number 2. Then we have Bob, which is at position 0. And finally, we have Ruth, which is missing from our list, which should return minus 1. And if we run it, we get 5, we get 2, we get 0 and minus 1, showing that our algorithm is correct. So basically this is the iterative implementation of the binary search algorithm. It has a runtime complexity of order log n, and what we will do in the next video is show how we can implement this algorithm in a recursive manner and also explain the reason why the algorithm has a logarithmic runtime complexity. Hello, in this video we will re-examine our binary search algorithm by writing a recursive version of it. And we will also try to understand why this particular algorithm has a logarithmic runtime complexity. It helps to understand this algorithm better by thinking about our problem space. Our problem space is the size of our input list. This is the list of names that we have to search in. In this particular example, the one we used in the previous video, initially this problem space is of 9 items. N is equal to 9. The size of our problem space is dictated by the pointer's position. Initially, the start and end pointer are on the first and last item of our input, so this is why initially our problem space is of 9 items. So once we compute the middle pointer and then we move the start pointer to the next item after the middle pointer, our problem space goes down to just 4 items. This is roughly the size of n division by 2. Every time we move the start or the end pointer, we are halving our problem space. In reality, this is actually n division by 2 minus 1, right? We are also reducing the space by 1 item. But if we ignore that minus 1, we are roughly reducing the space by halving it. It helps to think about this problem as after we halve this input array, we refeed it to our algorithm. We do the same operation that we saw before, the one where we find the middle pointer to be between the start and the end, and then again we perform the same operation of moving either the start or the end pointer. And after we move the start or the end pointer, our problem space again halves one more time. We have n division by 2, division by 2 again. So if you are following, we are always reducing our input size by 2. Let's now move on to the code to write a recursive version of this algorithm so you see that the size is kind of reducing by 2 every time. I have created a file called binary search recursive, and again you can find this file in the logarithmic directory. Let's move on to the code, and again we are going to write the same function signature binary search, and this time it will accept a few different parameters. The first parameter is the list of items that we're looking for. We call this parameter items. Then we are going to accept x, the item that we want to search in this list of elements, and then we have a start and an end pointer. When we call this function the first time, we set start to be a pointer to the first index in the list and end to be a pointer to the last index in the list. Inside this function, we will compute the middle pointer. We say mid is equal to start plus end division by 2. It's the same formula that we used in the iterative version of this function. And then because this is a recursive function, we need to write a stopping condition. The stopping condition is when we haven't found what we're looking for. If you recall from the previous video slides, this is when the start pointer is past the end pointer. When this happens, we just need to return that we haven't found the item. We return -1. Otherwise, if x is greater than the items at position mid, the middle of our problem space, this means that we need to have our input list with the right side of our list. And how do we do that? We just update the start and the end pointer. And after we have this list, after we take the right part of our input list, we need to refeed it back into this binary search function. So we can do our recursive call, binary search, we pass in the items list, x, again the same item that we're looking for, and we are going to take the portion of the list on the right of our mid pointer. We say mid +1 and end. We're using these pointers to simulate as if we are chopping our input list in half and feeding it again to the same function. And we must remember also to return whatever value this recursive call is giving us. We have another else if condition over here, and this time it's when x is less than items at mid. We just need to do the reverse. This time we take the left portion of our input list. We say binary search items and x. We leave the start as it is. However, this time we update the end pointer to say mid -1. This is kind of simulating chopping our input list in two and taking the left part of our input list. And again, we need to return whatever value this binary search is returning. Otherwise, our final condition, this is when x is equal to the items at mid. This is when we have found the item that we're looking for. And in that case, we just return the value of mid, giving us the location of the item that we were looking for. And I'm going to paste a few examples, the one we saw in the previous video as well, the same list as we had in the slides, and with the same examples as well. And if I run it, it gives me the same results that we saw in the previous video, just to show you that this recursive function is also correct. Just for you to understand how this recursive function works, let's move over here. I have another file called recursive steps, and it's the same algorithm exactly as we have implemented, the one where we are computing the mid, then with the stopping condition and the 3 different cases that we have. The only difference over here is that I am printing things as we go along in this function, just to show us what this function is doing underneath. And over here I have the same input list with all these names, and I'm going to look for the name rows. And as you can see over here, I am passing 0 as the start pointer and the index of the last item in our list, length of names -1. And if we go ahead and run this, it's going to print saying search for rows in, and gives me the whole problem space, right? The one with Bob, Isabel, James, and so on. The input list with 9 names. And if I press enter over here, it moves on to the next step, where it says I have computed the middle pointer and it is pointing on Peter. right? So mid, the variable, is currently on Peter, just as we have seen in the slides. And then it says Rose is greater than Peter alphabetically, right? So we need to take the right side of that input. We take Rose, Sam, Vera, and Zoe. And with this sublist, we do the recursive call. And again, it finds out the middle point. So it says middle point is Sam, Rose is less than Sam. And now we take the left part of this list, the items before Sam, which in this case, it is just the list with the item Rose in it. And now finally it's going to say middle point is Rose. And then finally Rose was found at position 5. And 5 is the return value of our function. This is just for you to try to understand how the recursive function calls. We are always kind of dividing our input list in two until we find what we're looking for. Let's move back to the slides and try to understand why this algorithm is logarithmic. Both the iterative and the recursive version of this algorithm have the same runtime complexity, that of log n. And this is because they start with n items in their input, and then in one step, they divide that problem space in two. We get n divided by 2. And again, this is divided further, n by 2 by 2, and so on until we find what we're looking for, or the result is 0, meaning that the item we're looking for does not exist. Every time we are subdividing the problem space is one step in our algorithm. So the number of divisions that we do is the total number of steps that our algorithm takes. Each time in each step, we do a constant number of operations. And for this reason, this algorithm has a runtime complexity of log to base 2 of n. This is the reverse of the exponential runtime complexity. Whenever you see this pattern of our problem space being reduced by a ratio, as long as each operation between this reduction is constant, you will have a logarithmic runtime complexity. Over here in this chart, on the green line, we can see the logarithmic function being plotted. As you can see, as we increase the size of n, the number of operations performed does not really increase that much. It's almost constant. Compared to the quadratic or even the linear, there is a huge difference. For example, over here, when just the input size is 40, we perform more than 4 times less operations than the linear one. And of course, the larger the input, the parameter n, the larger this gap is going to be. And let me give you a few concrete examples of comparing the linear algorithm with the logarithmic one. And in these examples, I am going to assume that each step takes approximately 1 second, just to simplify things. When n equals 4, the linear algorithm will take 4 seconds because it's doing 4 steps. However, the logarithmic one will take 2 seconds, so already we are twice as fast. When n equals 8, the linear one is 8 seconds and the logarithmic is just 3 seconds. You can see over here that even though we have doubled n, our input space, the time that it took did not double at all. Let's take an even larger example. When n is equal to 11,000, our linear algorithm will take 3 hours. However, our logarithmic one will just take 14 seconds, so the gap is now huge. And to take an even more extreme example, if we have n is equal to 8 billion, the linear one, assuming that we take 1 second for each step, it will take 254 years. However, the logarithmic one will compute in 33 seconds. So you can see over here, logarithmic algorithms are very, very scalable. You can give these algorithms huge input sizes and it will hardly affect their performance. And in fact, if you have ever used a database, you know that if you have a very large set of data in the database, the performance does not degrade linearly with the amount of data that you have. It does not really matter whether you have a few tens of rows in your database or whether you have millions, the database will still be quite fast if you are using the right indexes. This is because when you are querying a database by using an index, the search will take logarithmic time. Hello and welcome. In this video we will talk about the log linear functional class. If we had to list all the functional complexity classes, starting from the more scalable to the less scalable, we would have the constant class at the very top, then followed by the log, then the linear one, then this log linear one. After that, we will have the quadratic, and finally, we would have the exponential class. The log linear class that we shall see in this section sits right in the middle of this classification, sits more or less between the linear and the quadratic complexity class. In the previous section, we saw the logarithmic runtime complexity, and we also talked about the binary search algorithm where the problem space was divided in two on every step in our algorithm. The number of steps that we did was proportional to log of n. The algorithms in this log linear class are similar to this. However, at each step where we are doing this division, where we are reducing our problem space by a ratio, we also perform a linear operation where we do a number of operations that is equivalent to the input size n. This gives us the result of n times log n, which is the functional complexity class that we are talking about in this section. Let's look at an example that belongs to this complexity class, and one of the most famous example is the merge sort. In the merge sort, we have a list of numbers or any other items that can be ordered, like names, for example, and we want to produce a sorted list from this input. The merge sort is a very efficient algorithm on how to do this. In fact, it is one of the fastest algorithms. It belongs to a class of algorithms called divide and conquer, and these divide and conquer algorithms have 3 steps in their logic. The first step is to divide the problem into smaller ones, and you keep on dividing the problem until you can conquer it, until the problem is small enough that you can solve it easily. And the final step is to merge the different sub-solutions of your divided problem into a global solution. Let's have a look at how this merge sort works into these 3 steps: the divide, conquer, and merge. The first step is to divide. We have our input list of numbers over here. We just need to divide it in 2. In this example, our input list has 9 items. It's an odd number, so after we divide, and I chose over here to put the separator just before the 4, but you can also place it afterwards, it doesn't really matter, it will still work. So after we divide, we will get one list with 4 items and the other one with 5. And we can do this recursively. We divide the first list and the second one, again, more or less in the middle, and we have all these sub-lists. And again, we keep on dividing until we reach a list which has 1 item. We divide one more until they're all containing 1 item. This is our conquer step. When the list contains only 1 item, we can easily solve our problem. So the logic of the conquer step is that if the length is less or equal to 1, we can solve it. We know that a list with 1 item is already sorted. There's nothing to sort inside. So once we have conquered our sub-problem, we just need to merge the different sub-solutions together. This is the merge step. When we have 2 portions that are sorted, we can call them list A and list B, and we want to join them together so they are both sorted in one list. For the simple case, when we have 2 lists with just 1 item, it's easy to solve. You just pick the smallest one and you place it in front of the other. However, we want to solve it for the general case, when we have 2 lists with 2, 3 or more items and we want to merge them together. So let's have a look at another more complicated example when we have a list with 4 and 5 items and we want to merge them together. The algorithm to merge these 2 sub-solutions is to have 2 pointers, and we can call them L and pointer R. We place them on the front of each list, on the first item on each list, and we compare the value at each pointer with each other. We pick the smallest one, in this case 1 is smaller than 4, and we place this value at the front of our list. After we pick this item, we need to advance its pointer. In this case, we advance the left pointer forward, so it's now on item 2. Again, we compare 2 and 4 together, we choose 2, so we write it on our output list, and we advance the left pointer. Once more, we compare 3 and 4, 3 is smaller than 4, so we write it on our output list. We move the left pointer forward one more time, and this time we have 5 and 4. And 4 is smaller than 5, so we write 4 on our output list, and we move the right pointer forward instead of the left. And this time we compare 5 and 6, 5 is smaller than 6, we write this down, and we move the left forward outside the bound of our first list. When this happens, when we are outside the bound, we assign the value to be infinity. And this way, any number that we have left on the other list will be read and written onto the output list. So in this case, 6 is smaller than infinity, we write it on the list, we move the pointer forward. 7 is again smaller than infinity, we write it on the output list, move the pointer forward, and so on. Then 8, then 9, and then finally we are complete once we have the output list filled up with all the numbers. We have merged the two lists together in one global solution. What we will do in the next video is break down this algorithm in code and implement each step, the divide, the conquer, and the merge, one at a time. Hello, in this video we will look at the implementation of the merge sort, which is a log linear algorithm. Over here I have created a file called mergesort.python and I've placed it in the log linear directory. Let's move on to the code and start by implementing the hardest step in our algorithm. If you recall from the previous video, the algorithm is a divide and conquer algorithm and has 3 steps. It has a divide, a conquer, and a merge. And the merge is the slightly tricky part of this algorithm. So let's start from this step. Let's define a function called merge that accepts 3 parameters. If you remember from the previous video, the merge function takes 2 arrays and joins them together. This first parameter, the items parameter, is the 2 lists joined together in a sorted fashion. The next parameter, we call it left. This is the left half of the split array that we want to merge. And the next parameter is the right. This is the right part of the split array that we also want to merge into the items list. Let's start by creating the left and the right pointer. I call them L and R and assign them the initial value of 0. This pointer will point to each item from the left and the right list, and we will increment the pointer depending on which item is bigger. So let's implement this logic by using a loop which says for I in range of length of items. In this loop we are going to perform a number of steps which is equivalent to the length of our output list, the list items. This is because at each position in this list we need to choose whether we take an item from the left list or the right one. So inside this loop we say value left is equal to left at L, and then we say value right is equal to right at R. We are simply reading the value at the 2 pointers, at the left and the right. We have to be careful here because the left pointer might go outside the bounds of our left or right list. And when that happens, we should assign the value of infinity to these variables so we can choose the other one. So here we can simply add an if statement to say if L is less than the length of left, then we should choose it. Otherwise, we should assign the value of mat.infinity. And we can do the same thing on the right side as well. If R is less than length of right, else mat.infinity. Now it's just a matter of picking up the smallest of these two. We say items at I is equal to the minimum between the value left and the value right. And the final step, we need to advance either the left or the right pointer depending on which one is smallest. So we say if value left is smaller than right, we should advance the left pointer. So we say left plus 1, otherwise right plus 1. And at the end of this function, we simply need to return the items list. The items list will contain a sorted, merged list from the left and the right. Let's now write the main function that will do the other 2 steps. Let's call this function mergesort, accepting a list of unsorted items. In this function, we will do the other 2 steps, the divide and conquer. Let's start from the divide step. We say mid, this is the point where we are going to divide the list into, is equal to the length of items divided by 2. And then we say left is equal to items ending at this mid pointer. This is the way we slice the list at mid and take the first part, the left part. And then we do right is equal to items mid till the end. We take the remaining part, the right side of this division. After we slice these 2 portions, we should continue slicing them into smaller chunks, always taking the left and the right. And we can do this recursively by calling the merge sort function first on the left part and then also on the right part. And since we are constantly dividing the list in two, we need a stopping condition. This is the conquer part. This is when the list becomes small enough that it is already sorted, when we have 1 or 0 items. So we can say if length of items is less or equal to 1, then we return items. Again, this is our conquer part. And finally, once we have a sorted left and a sorted right, we should merge the two. We say merge items left and right, and we return the solution. Let's try it out. I have here a few examples. The first list that we have is just a randomly ordered list with just some numbers, and the second list is an ordered list from larger to smallest. If we run these two examples, you can see that the output is correctly sorted. If you have never seen the merge sort algorithm and this is your first time, I would suggest that you spend some time trying to understand the algorithm, especially because it involves recursion. If you're not very familiar with it, it's a useful algorithm to know because sometimes it comes up in coding interviews. What we will do in the next video is analyze this algorithm and understand why it is log linear. And later we will compare log linear algorithms with quadratic. Hello, in this video we will analyze the merge sort algorithm and we will find out why it has a log linear runtime complexity. We'll also compare the log linear functional class with other functional classes like the linear and the quadratic. Over here I have the algorithm that we have developed in the previous video, and as you know, it's this split in three. It has the divide, the conquer and the merge parts of the merge sort algorithm. If we have a look at the merge part, at the merge function, we have inside this main loop that iterates over the length of our output list, the items list. This means that it's scaling proportionally with the size of our output, with the sum of the left and the right items together. This gives it a linear runtime complexity. So this part of the algorithm has a runtime complexity of big O of n. If we look now at our main function, the merge sort that accepts this list of items, we need to analyze how many times we call this merge function. Now this merge function is called for each split that we have in the array. As we go down our recursive stack of the number of times that we are splitting our input list, we are calling this merge function with the left and the right parts of the split. So for example, if we pick the last level where we have the left and the right parts of the list just containing one item, we are calling this merge function for half of the size of our input list. And each time it outputs a list with two items. So if you think about it, at this level, at the last level, we are calling it n division by 2, n being the size of our array. But each time we are merging two items together, meaning that it takes two operations, and 2 times n division by 2 gives us n. So at this level, we are calling it n times. If we look at other levels, it's the same story. For example, at the top level, when we have two half lists containing each one of them n division by 2, here we are calling the function once. However, it is iterating over every single item of the left and the right, giving us n number of operations. So at each level, we are performing n operations, whether it's the last one or the first one. So now it's just a matter of finding how deep our stack is, the number of levels that we go down. And if you recall from the previous section when we were doing the binary search, this depth is equal to log 2 base 2 of n. This is because we are dividing by 2 every time. We are splitting the list in 2. So this means that our final runtime complexity is n, the step for the merge sort, multiplied by log of n. This is our final complexity for the merge sort. I also want to give you a feel of how fast an algorithm that runs n log n is. If we have a look at this graph, you can see that the log linear complexity is kind of in the middle of everything. On the fast side, we have the logarithmic complexity, then we have the linear, then we have the log linear, quadratic, and finally the exponential. However, this graph is a little bit misleading because it makes it look as if the log linear is kind of in between the quadratic and the linear one. However, it is much closer to the linear one than it is to the quadratic. And instead of zooming out of this graph, I'm going to show you the performance difference between a quadratic and the log linear with an example that we have seen in a previous section. If we go back to the code, I have here under loglinear created a new Python file called closespair, and this is a different implementation of the algorithm that we saw in the quadratic lesson. Recall, in the quadratic lesson, we were trying to find from a list of points 2 points that were the closest together. This is another solution of that problem using a different algorithm. In fact, this algorithm is also a divide and conquer algorithm, which happens to have a runtime complexity of n log n. Recall that the previous algorithm had a quadratic runtime complexity. I will not step into a lot of detail from this algorithm because it is a little bit complex. However, just to give you some introduction, here it is sorting all the points by x, then we sort all the points by y, and then we have this recursive function that is following the same paradigm that we saw in the merge sort, the divide, conquer, and merge. If we look into more detail, you can see over here that the conquer part of the algorithm are these two if statements. The divide part is this part over here where we are dividing the list of points that we have in the middle. And then the merge part is this part over here. The merge part is always the slightly complex part of a divide and conquer algorithm. In this case, it's using a geometry trick to find out the closest pair in a subset of points. And the point of this is to show you how much more performant a log linear algorithm is than a quadratic one. So if we switch to the radar window Python, this is the program that we saw in a previous section, the one that prints the points on a window and finds the closest pair. Over here you can see we're still using the quadratic version of this algorithm, and if we scroll down we are going to generate 8,000 points and find the 2 points that are the closest together using the quadratic algorithm. Let's run it. Let's wait a couple of seconds until we plot all the points onto the screen. In this case we have 8,000 points, and if we hit run to find the 2 closest pair, it's going to take a while. And in fact, as usual, I am going to fast forward the video so you don't have to wait for too long. And once it completes, it has found the 2 closest pair. And if we exit this window over here, it tells us that it took 28.3 seconds. Now, if we go back to our code and instead of using the quadratic version, we use the log linear algorithm, the one I have just showed you, the one that's using a divide and conquer algorithm, and we go ahead and run this. Again, we have to wait a couple of seconds until we generate the 8,000 points. And as usual, let's hit run. As you can see, it was instant, okay? I didn't have to fast forward any video, it just happened immediately. And if we close this window, it tells us the time it has taken to compute the closest pair. In this case, it is less than a second. It's in fact 0.098 seconds. So much faster than the 28 seconds that we had for the quadratic version. So I want to conclude this lesson on this point that actually choosing the right algorithm for your problem will make a huge difference in terms of performance and scalability than if you had to use other techniques, like for example getting a faster computer or using multi-threading techniques and so on. So the lesson here is that if you have a difficult problem to solve, especially one with a huge input, research a little bit about which algorithms you can use. Most probably someone else has already solved that problem, and understand the runtime and memory complexity of that solution, and then choose the best algorithm that fits your scenario.